Network Infrastructure and Design, Network Models, the TCP/IP model. Whereas in the previous module, we talked about the OSI model, a mostly theoretical model that's in use in computer networks. In this module, we're going to talk about perhaps what is considered to be one of the most common, or at least the most widely used model, the TCP/IP model. Now, while it's important that we memorize and familiarize ourselves with the OSI model, it's also really important that we understand this TCP/IP model and the differences between it and the OSI model. As technicians and administrators, it's really important that we're familiar with each layer, as well as how data transfers between all of these layers, and how all the protocols that are used in TCP/IP relate to one another and in the layers. So, the objectives of this module are first to explain the purpose and depth of the TCP/IP model and to compare it in some ways with the OSI model. We're also going to talk about what data encapsulation and fragmentation are. These are really key to how large amounts of data are able to be transmitted and transferred over the internet, the largest network in the world. And then we're going to talk about the four layers of the TCP/IP model, beginning with the fourth one, and then the third, the second, and the first. Finally, we're going to talk about protocol binding and something called an MTU black hole that doesn't really occur much anymore, but that Network Plus wants you to be familiar with. So, as mentioned before, the TCP/IP model is perhaps the most widely known or used networking model. It's another networking model that's most commonly defined using abstract layers, just like we had with the OSI model. Now, the entire purpose of this model is to allow for conceptualization of how a computer network functions in maintaining hardware and protocol interoperability. Also, it's commonly called the DoD model for the Department of Defense, which funded much of the research that went into it. TCP/IP was permanently activated in 1983, and it's been in use just about ever since. Now, it wasn't until 1985 that this model was actually commercially marketed, but it is now the preferred network standard for protocols and so on. Now, this means that using these four layers on this model, the bottom being the network interface layer, the internet layer, the transport layer, and then finally the application layer. And if you know or remember the OSI model, you'll see that there is some resemblance. Understanding this model and understanding how data flows is actually how the entire world is allowed to communicate and connect to the network. So this is necessary for every computer in the world that is currently using the internet, and for the most part that's on any network. We might find other smaller, lesser known protocols that do operate outside of this, but I think you would be hard-pressed in today's day and age to see that. So technicians and engineers will probably sit and talk about technology's implementation of these two models for hours on end. And the reason is because there's quite a bit of history and brilliant thinking that went into the creation of both of them. The TCP/IP model was, in fact, created before the OSI model, and it still makes it easier to represent how communication and network-related protocols are defined and relate to one another. However, it's still more common to hear technicians and administrators use the OSI model when they're troubleshooting or referencing networking devices. And there are many similarities between the two models. The first similarity is the obvious use of the layers to describe the functions of these communication systems. Although in TCP/IP we have 4, whereas in OSI, as you recall, we have 7. Some of them even have similar names, as you can see, from application and transport, and then we see network or internet and network interface, which is very much like physical. In some ways, some people consider the TCP/IP model to be a smaller version of the OSI model. However, this leads to some misconceptions about the position of relationships of certain protocols within the OSI model. Because these are two very different designs and they have different purposes, there are some recognizable similarities, but they're still, at their core, different. So the purpose of this OSI model was an attempt to simplify and standardize networking. TCP/IP's original purpose, as opposed to the OSI, is more attempting to sort out the internet protocols into comprehensive groups according to their functions of the scope and the sort of network that's involved. Now, one of the similarities between the two models is they both have interchangeable network and transport layers. Also, each layer of the OSI model directly correlates with the TCP/IP model. Now here you can see the application layer, the presentation layer, and the session layer of the OSI model correspond to what we know as the application layer of the TCP/IP stack. This means that everything in the OSI model that fell into application, presentation, and session are actually done in the application support block. Next, the transport layer of the OSI model corresponds directly to the transport layer of the TCP/IP model, the network layer of OSI with the internet layer of TCP/IP, and that is easy to remember since internet is really short for like internetworking. And the data link and physical layers of the OSI model correspond directly to the network interface layer of the TCP/IP. Now, some of these correlations, it should be mentioned, aren't precise and exact. They're sort of approximations, and that's because they are two very different models, and therefore they were created differently and weren't necessarily created with the one or the other in mind. That being said, TCP/IP and OSI were built with knowledge of one another, and so we do see this overlap. Now, the TCP/IP model outlines and defines the methods data is going to flow in a communication system. It does this by assigning each layer in the stack specific functions to perform on the data. And ultimately, each layer is completely independent of all the other layers and more or less is unaware of the other layers. For instance, the topmost layer, the application layer, is going to perform its operations if the processes on the communicating systems are directly connected to each other by some sort of information pipe. The operations that allow for the next layer, the transport layer, to transmit data between the host computers is actually found in the protocols of lower layers. And from there on, each data layer will complete its specified actions to the data and then encapsulate the data, where it's then passed down the stack. In the opposite direction, when data is traveling back up the stack, and we saw the same thing with OSI model, the data is then de-encapsulated. So when it's going down, we call that being encapsulated. And when it's going back up, we call it de-encapsulated. So we really need to understand how all of this works together in order to get a really strong picture of TCP/IP and be able to speak about the layers in general. So let's talk about encapsulation. Each layer is responsible for only the specific data defined at that layer, as we've said. Now, these layers are going to receive the data package from the layer above it when sending, and the layer below it when receiving. This makes sense. If I'm receiving data, it's going up, so the data is coming from below, and if I'm sending, it's going down, from the application down to the networking interface. Now, when it receives this package, each layer is going to add its own packaging, which is called a header. This header is used by the corresponding layer at the receiving side for specific purposes. The exact purpose is really going to depend on the layer in question. But this header is going to be added to the beginning of the data so that it is the first thing received by the receiving layer. That way, each layer on the receiving end can then remove that header, perform its operations, and then pass the remaining data up the stack, up the TCP/IP model. On the lowest layer, a footer is also going to be added. And this is going to add to the frame by adding more supplemental information. This extra data at the end of the data package is going to assist the receiving end on ensuring that the data was received completely and undamaged. This footer is also what's called an FCS, or a frame check sequence. And as the name implies, it is going to check to make sure the data was received correctly. Now, on the receiving end, this process is reversed by what's called de-encapsulation. In other words, the data is received at each layer and the headers are removed to allow the data to perform the related tasks, where finally the data is received by the application layer, and then the resulting data is delivered to whatever the requested application was. Now, just like with the OSI model, and we'll talk about later, this application layer doesn't mean the actual application itself. It's simply the layer that provides access to the information from an application. Now, just like the OSI model, there are a few mnemonic devices that can be used to help in remembering these layers in order. And the one that I use the most, going from the top down, is called All Things in Networking. Again, that's application, all, transport, things, internet, in, network interface, networking. So now we have a better understanding of how the data is going to proceed from layer to layer through encapsulation, going down from application to transport to internet to network interface, right? And then through de-encapsulation, which goes the opposite way. Let's take a closer look at these layers, starting with the topmost layer, the application layer. So here on the application layer, much like the application layer of the OSI model, we find what's considered the highest level protocols. Higher level meaning these protocols such as SMTP, FTP, and so on. These protocols are not necessarily concerned with the method by which the data arrives at its destination, but simply that it just arrives, period. Here in the application layer, we also provide the functions that relate to the presentation and the session layers of the OSI model, as we've already pointed out. It does this typically through the use of what are called libraries, which are collections of behavioral implementations that can be utilized and called upon by services that are unrelated. So this means that the application layer of the TCP/IP model encodes the data and performs any encryption and compression that's necessary, as well as initiating and maintaining the connection or the session. As we can see here, these are just some of the protocols that we find at the application layer. We can also further group some of these applications based on the specific type of function that they provide. For instance, if we're looking at protocols that are dedicated to transferring files such as FTP or TFTP, which if you recall is the trivial FTP, then there are also protocols that can be categorized by supporting services. So some of those are going to be, for instance, DNS, the domain name service, and SNMP, which is for management purposes, or even BootP, or the bootstrap protocol. Now, just like the OSI model's application layer, this TCP/IP application layer is responsible for process-to-process level data communication. This means that the application itself doesn't necessarily reside on this layer. What it more means is that it defines what the application or what type of application can be utilized depending on the protocol. So for example, SMTP specifies that outgoing mail communication with the mail or exchange server, and IMAP specifies the incoming mail communication with the mail server. Also, remember that only those applications that are network relatable are going to be managed at this layer, not necessarily all application. So this layer's role is more towards software applications and protocols and their interaction with the user. And it's not as concerned with the formatting or transmitting the data across the media. For that, we have to move lower down into the model and get to the transport layer. Now, on the transport layer of the TCP/IP model, we have two main protocols that we need to be familiar with. First, we have the Transmission Control Protocol, or TCP, and the second is the User Datagram Protocol, or UDP. Let me just write those out here so that you can see what these stand for. Again, now on this layer, three things are going on. Data verification, error checking, and flow control. Now, our two heavy-hitting protocols are done in very different ways. So TCP/IP, as we've talked about in the past, is what we call connection-oriented, which means there's a guaranteed delivery, whereas UDP is connectionless, which means it's just a best effort delivery. UDP doesn't have any means of error checking. That's one of TCP's areas of expertise. So to put TCP and UDP in perspective, I've always thought about it as if, say, a grade school teacher needs to send a note to a student's parent because the student hadn't turned in their homework for more than a week. Now, the teacher can send the note one of two ways. The first is through UDP, or the uninterested, doubtful preteen. Now, this UDP is certainly going to make it home as quickly as possible, but whether the message gets sent to the parent or not really isn't UDP's biggest concern. Getting there quickly is. So UDP is going to have you that quick, but not necessarily guaranteed. Now, meanwhile, the other method, TCP, or teacher calls parent, this is the way the teacher has a guaranteed delivery of the message. But if parents aren't home, the message cannot be delivered, or something happens during the communication process, TCP will wait and attempt to send the message again. So, whereas UDP is quick, TCP is guaranteed. And so that's sort of the give and take there. Now, while our story is a generalization, it really touches on the two most important characteristics of these protocols. Now, there are a few other specifics about TCP that are really worth mentioning. Firstly, and most importantly, we have reliability, like we just mentioned. How it accomplishes this is TCP assigns sequence numbers to each segment of data, and the receiving end looks for these sequence numbers and sends what's called an ACK, or acknowledgement message, which is something important that you do want to be familiar with, and you might also see that as a SYN-ACK, which is the synchronization, and that ACK message is sent when the data is successfully received. Now, if the sending transport layer doesn't receive the ACK or acknowledgement message, then it's going to retransmit the lost segment. Secondly, we have data flow control, which we've already mentioned. This is important as networking devices are not always going to operate at the same speeds, and without flow control, slower devices might be overrun with data, causing network downtime. Thirdly, we have something called segmentation, and segmentation occurs at this layer, taking the tedious task away from the application layer of sectioning the data into pieces, or segments. These segments can then get sent to the next layer below to be prepared for transmittal across the media. So the final consideration for TCP is, in order for an application to be able to utilize this protocol, a connection between port numbers has to be established. The devices try to create this session using a combination of an IP address and a port number. Now, this combination is called a socket. In the future modules, we're going to look at referencing TCP and UDP, as well as going a bit more further into explaining how they function and interact with different protocols. But what you see here is the IP address on a specific port number. So we know, based on this port number, what the connection is trying to attempt. And whether or not it's TCP or UDP, we know whether it's connection-oriented or connection-less. The internet layer of the TCP IP model corresponds directly to the network layer of the OSI model. Now, the data terminology on this layer, as I think we discussed when we talked about the OSI model, is a datagram. Now, as the internet layer relates directly to the network layer, which, if you recall, was layer 3, we can a little more easily understand a few things that happen on this layer. First, it tells us that this layer is responsible for routing. If you recall, layer 3 devices for OSI are routers. This means that it ensures the typically fastest and best path from the source to the destination. This layer is also responsible for data addressing. And if you recall, with data addressing, we're dealing with the second part of TCP IP, which is the Internet protocol, aptly named since it is on the Internet layer. Now, the Internet protocol is responsible for a couple main functions. The first of those functions is what we call fragmentation. It's important for us to understand something called MTUs, which are maximum transmission units. so that we know why fragmentation has to occur. Now, the MTU is the term, as the name implies, that's used to define the largest size of increment of data in bytes that can pass through the given network device, such as a router. Now, often data is going to need to pass through networks with MTUs that are less than the MTU listed on that device. Generally, even not just match to, but the lower it is, the more it's preferred, because then we can make sure that it's not going to have a problem. So network devices are going to send and receive messages or responses to datagrams that are larger than the device's MTU. In these instances, when there is a datagram that's larger than the MTU of a device, the transmitting internet layer fragments the data, or the datagram, and then tries to resend it in smaller and more easily manageable blocks. So once the data is fragmented enough to pass through the remaining devices, the receiving end's internet layer then pieces together those fragments during the reassembly process. Now, in the header of those fragmented datagrams, if we go back just a bit, you'll see right here, the header, there's a specific field that's set aside for what we call 3 flag bits. The first flag bit is reserved and should always be 0. The second is the don't fragment, or the DF bit. Now, either this bit is off, or 0, which means fragment this datagram, or on, meaning don't fragment this datagram. The third flag bit is the more fragments bit, MF. And when this is on, it means that there are more fragments on the way. And finally, when the MF flag is off, it means there are no more fragments to be sent, as you can see right here. And that there were never any fragments to send. So as we see here, our initial datagram that we wanted to transmit had an MTU that was too large to send. It was 2500. And it was too large, therefore, to go through router B. And so then we fragmented this datagram and added those bits to the headers of the fragments. So that's how this all works, and that's why fragmenting is so important. Now let's take a look at a networking problem that used to plague network engineers and technicians that has to do with MTUs for some time. And this is also something that's specifically called for on the Network Plus exam. Now, a black hole router is the name given to a situation where a datagram is sent with an MTU that's greater than the MTU of the receiving device, as we can see here. Now, when the destination device is unable to receive the IP datagram, it's supposed to send a specific ICMP response that notifies the transmitting station that there's an MTU mismatch. This can be due to a variety of reasons, one of which could be as simple as a firewall that's blocking the ICMP response. And by the way, when we talk about ICMP, we're really talking about the ping utility as well. Now, in these cases, this is called a black hole because of the disappearance of datagrams. Basically, as you can see, I'm sending the data gets here. The device, the router here, says, wait a minute, I can't fit that 2500 MTU through my 1500, sends a response, but for some reason the response hits this firewall and doesn't make it back to the router, and so the data is lost into this black hole. Now, this is called a black hole because this datagram disappears as if it were sucked into a black hole. Now, there are some ways to detect or find this MTU black hole, and one of the best ways is to use the ping utility and specify a syntax that sets the MTU of the ICMP echo request, meaning you tell it, I want to ping with this much of an MTU, and so then we can see if the ping's not coming back. If it's coming back at one MTU and not another, then we know, oh, this is what's happening right here, and we can determine where the black hole is specifically occurring. Now, on the bottom of the TCP/IP stack is the network interface layer. Now, this layer is completely dedicated to the actual transfer of bits across the network medium. The network interface layer of the TCP/IP model directly correlates to the physical and the data link layer of the OSI model. Now, the data type we're going to be talking about on this layer are what we call frames, as opposed to datagrams. Now, the major functions that are performed on this layer, on the data link of the OSI model, are also occurring at this layer. So we're really talking about switching operations that occur on layer 2, which again is that data link layer. And so this is where we see switches operating. Which means that we're really dealing with MAC addresses. Okay? Now, a MAC address, again, is a 48-bit hexadecimal, universally unique identifier that's broken up into several parts. The first part of it is what we call the OUI, or the Organizational Unique Identifier. This basically says what company is sending out this device. And then we have the second part, which is the NIC specific. And then we have the second part, which is specific to that device itself. So this is the manufacturer, and this is for the device. You can literally go online, search for this part of the MAC address, and it'll tell you what company is creating this device. Now, the easiest way to find the MAC address in a Windows PC is by opening up the command prompt and using ipconfig all, which we've talked about in A+. This brings up the Internet Protocol information, the IP address, and it also brings up the MAC address or the physical address that's assigned to your NIC. So now that we've covered the MAC address it's really important to understand the parts of an Ethernet frame. And remember, we're talking about frames at this juncture. So the preamble of an Ethernet frame is made up of 7 bytes or 56 bits, and this serves as synchronization and gives the receiving station a heads up to stand by and look out for a signal that's coming. The next part is what we call the start of frame delimiter. The only purpose of this is to indicate the start of data. The next two parts are the source and destination MAC addresses. So the Ethernet frame, again, this is everything that's going over this Ethernet, over the network. We have the preamble. It says, hey, pay attention now. This that says, now I'm giving you some data. And then we have the destination and the source MAC addresses, so that way we know where it's coming from, who it's going to. And this takes up 96 bits or 12 bytes. Because remember, this is 48 bits right here. So if we double that, that's going to be 96. And then the next type is what's called the frame type. This is 2 bytes that contain either the client protocol information or the number of bytes that are found in the data field, which happen to be the next part of the frame, which is the data. This field is going to be a certain number of bytes, and the amount of data is going to change with any given transmission. The maximum amount of data allowed in this field is 1500 bytes. We can't have more than that. Now, if this field is any less than 46 bytes, then we have to actually have something called a pad, which is actually just going to be used to fill in the rest of the data. And the final part of this Ethernet frame is called the FCS, or the frame check sequence. And this is used for cyclic redundancy check, which is also called CRC. This basically allows us to make sure that there are no errors in the data. Now, similar to the way that an algorithm is going to be used to ensure integrity of data, the CRC uses a mathematical algorithm, which sometimes we're going to refer to as hashing, which we'll talk a lot more about when we get to Security Plus. That's made before the data is sent, and then it is checked when it gets there. That way we can compare the two results bit for bit, and if the two numbers don't match, then we know the frame needs to be discarded. We assume there's been a transmission error, or that there was a data collision of some sort, and then we ask the data to be resent. Now, this layer, by the way, this network interface layer, is also responsible for the network access control, and some of the protocols that operate on this are what are called point-to-point protocols, ISDN, which is which we've talked about, also a type of network, and also DSL. So these are some of the things that exist at this, and this makes sense because, again, we're dealing with the physical bits, bytes of data. So now that we've taken a look at each of the layers in the TCP/IP model, there's still a couple things that we still need to define. Now, we've discussed how some of the protocols that we've seen relate to the OSI model as well as the TCP/IP model. And we found that some of the protocols function much more smoothly when they're put into the context of an outline of one of these models. So the next definition I want to make sure to cover is something called protocol binding. This is when a network interface card receives an assigned protocol. It's considered binding that protocol to that NIC. So just as we learned how the data is going to be passed down from one layer to the next, it's very important that we have these protocols bound to the NIC. We can have multiple protocols actually bound to one network interface card. Now, of course, we can most easily recognize these when we're looking at the IPv4 and IPv6 configurations in our network connection properties or adapter settings in Windows. If, for instance, you use a specific protocol more than others, and you're confident in the stability of the connection, you can change the order of binding to potentially speed up your network, since what it basically does is it's going to give a list of each protocol that exists, and it's going to hit each protocol one after the other. So if there's one that you use more, you can set that at the top so it doesn't have as far to go. So as we can see here, we have several default protocols, and they're going to be tested in order for that available connection. And the first protocol that's found to have a matching active protocol on the receiving end is going to be the one we use. Now, while this might sound like a pretty decent method of doing things, it also opens your computer up to utilizing a lesser protocol, which is potentially going to give you a slower speed. So the graphical interface or properties menu for your network interface card is where you're going to be able to configure all of this stuff such as TCP/IP, DNS server assignment, DHCP, and so on and so forth. So after all of this, it's really important to understand that all of this organizing, categorizing, defining of these protocols, the assigning of rules and roles, all of this, the internet didn't just happen overnight. It's not even necessarily the way we did it on purpose. These standards and these models are going to continue to expand and change, and eventually we might even have a brand new model that we're going to have to learn about. But in the meantime, these models are here to stay, and they're going to remain really important, and especially in the future, you have to understand the historical roots of the network so you can be able to define not only how to go forward in the future, but also how to prepare yourself for our Network Plus exam. So let's just go back over everything we've talked about one last time. We covered in a lot of stuff here, right? First, we explained the purpose of the TCP/IP model, and we compared the TCP/IP model with the OSI model. Remembering that the top three layers, if we look at this, if we do the 3, 2, 1, and then we look at 7, 6, 5, 4, right? 2 and 1, physical and data link, are going to go straight over here to that physical layer 1 of the TCP/IP model. Then the network layer is going to correspond directly to the internet layer. The transport layers are going to be the same. And session, presentation, and application all go over to the presentation layer in TCP/IP. We also talked about defining data encapsulation, and we walked through how fragmentation works on the internet layer. And the reason we need to do that is because of the maximum transmission unit. Finally, we talked about the fourth, third, second, and first layers of the TCP/IP model. And on each model, we outlined some of the important aspects of each layer, such as the application layer, which again is the way that the application is going to process all of this information. The transport layer, which is in charge of reliability. And it is where TCP, which is connection-oriented, or UDP, which is connection-less, live. And this is also going to deal with flow control and also segmentation. We looked at layer 2 as well, which is the internet layer, and the fragmentation that happens there. And network 1, the network interface layer, which is equivalent to all that physical stuff that we've talked about. We also looked at how the terminology changes. Remember, on layer 4, we're talking about data. On layer 3, we're dealing with segments. On layer 2, we're dealing with datagrams, also called packets. And we broke down then on layer 1 frames and an Ethernet frame and all the information that goes into that. Finally, we defined what an MTU black hole was, and we finished off everything by talking about protocol binding, which is binding certain protocols to specific NICs and in a delineated order. IP addresses and conversion. So welcome to this module. We're going to cover IP addresses and conversions. And in some of the previous modules, we talked about a lot of the technologies and theories and protocols that make up computer networks. And so here we're going to discuss some of the more important aspects of networking, specifically the IP address. So this module is going to begin by introducing us to some of the specific protocols that are found within the TCP/IP protocol suite that you need to know about for the Network Plus exam. And these are TCP and IP in a little more depth. We mentioned them briefly when we talked about the TCP/IP model. And then we're going to describe UDP, which is a connectionless protocol. Then we're going to look at ARP and RARP, two versions that allow us to basically, or two protocols rather, that basically allow us to map MAC addresses to IP addresses, and which are basically responsible for routing in general. And after that, we're going to look at two management protocols, one called ICMP, which I introduced to you in previous modules, and I said it was related to the ping utility, and we're going to learn a little more about that. And then IGMP, which is slightly different, has to do more with multicasting and unicasting. And then we're going to continue by outlining IP packet delivery processes, and we're going to finish off the module with a bit of an introduction into binary and decimal conversions, so that later on we can talk a little more in depth about IP addressing and how something called subnetting works, which is going to require us to understand the difference between these two ways of writing our numbers. And after we have covered all these topics, we're going to have a fundamental understanding of IP that's going to prepare us for some of the more in-depth topics, as I just mentioned, in the following modules. So let's begin by taking a look at two of the most important protocols that make up the suite, TCP and IP. Now, in previous chapters, we briefly described these two, but we still need to take a closer look at them to assure that we have a complete understanding of the many different protocols that are found in our protocol suite. So first, for those applications and instances that depend on data to be reliable in terms of delivery and integrity, the Transmission Control Protocol, or TCP, and I'm just going to write out Transmission Control Protocol, is a really dependable protocol and provides a number of features. First, it guarantees that data delivery, and besides guaranteeing that delivery, it also has a certain amount of reliability. It also offers flow control, which, as we've mentioned in the past, assists a sending station in making sure it doesn't send data faster than the receiver can handle. This function also is going to assist in the reliability of data because it ensures that there isn't any data lost due to overloading the receiving station. Now, TCP also contains something called a checksum mechanism. And what this does is it assists with error detection. And the level of error detection isn't as strong as that of some of the lower layers. And you recall that this is in the transport layer of the TCP IP stack. But it does catch some specific errors that may go unnoticed by other layers. And by the way, this checksum, basically, it sort of has a number that it creates based on the data, and it can check that number at the beginning and at the end to make sure we haven't lost anything. Now, this protocol attempts to alleviate MTU, if you recall what we talked about with MTU there, mismatches on the data link layer by establishing maximum segment sizes that can be accepted by TCP. This is also going to reduce what we talked about earlier, that MTU black hole. Now, further examining IP, or the Internet Protocol, which is aptly named and exists at the Internet layer, unlike TCP, IP is characterized as being connectionless, or a best effort delivery, which is also like UDP, which we'll see in a second. It outlines the structure, then, of information, which is called datagrams or packets, and how we're going to package this stuff to send it over the network. Now, this protocol is more concerned with source-to-destination navigation, or planning, or routing, as well as host identification and data delivery, solely by using the IP address. So this is slightly different from TCP, which is doing stuff in a much more different way. Now, IP is used for communications between one or many IP-based networks, and because of its design, it makes it the principal protocol of the Internet, and it's essential to connect to it. So unless we are using IP address in today's day and age, we will not be able to connect to this big thing called the Internet. Now, the terms connectionless and connection-oriented relate to the steps that are taken before the data is transmitted by a given protocol, whatever that protocol might be. With TCP, we're looking at connection-oriented, and of course with IP, we're looking at connectionless. And for instance, the connection-oriented protocol is going to ensure a connection is established before the sending of data, meaning it is oriented towards a connection, whereas a connectionless isn't going to. It doesn't matter if there is a connection established already. So the next protocol, which is also connectionless that we want to talk about, is something called UDP. Now, since we have many applications and their functions depend on data being sent in a timely manner, TCP and its connection-oriented properties hinder their performance. In these cases, we're able to use something called UDP, again, the user datagram protocol. And UDP is connectionless, just like IP is. And that means it's a best effort delivery protocol. So with TCP, if packets get delayed or if they're needed to be resent due to a collision, the TCP on the receiving end is going to wait for the lost or late packets to arrive. Now, with some sensitive data delivery, this is going to cause a lot of problems. And UDP is what we call a stateless protocol, which prefers the packet loss over the delay in waiting. So UDP is only going to add a checksum to the data for data integrity. It's also going to address port numbers for specific functions between the source and the destination. Nodes such as UDP port 53 for DNS, which is one that you should remember from an earlier module. Now, UDP's features make it a solid protocol, and it's used for applications such as VoIP or Voice over IP and online gaming. This makes sense because we don't care if every single little packet arrives. What we want is the speed with which UDP is going to deliver stuff. Obviously, if we miss a couple packets in voice, that's okay, they drop, but we don't want to have to wait until the next packet arrives. That's going to actually cause much more of a delay. And so we're going to use this one in more VoIP and online gaming purposes. Now, the next protocol we want to be familiar with is called ARP, and it's also necessary for routing. ARP, or the Address Resolution Protocol, and the Reverse Address Resolution Protocol are request and reply protocols that are used to map one kind of address to another. Specifically, ARP is designed to map IP addresses, addresses that are necessary to TCP/IP communication, to MAC addresses, which are also known, as we've discussed in the past, as physical addresses. And again, IP addresses work on the networking layer, or in TCP/IP, the internet layer, whereas MAC addresses operate on the network interface layer of TCP/IP, which in OSI would be the data link layer, layer 2. Now, in TCP/IP networking, ARP operates at the lowest layer, the network interface layer, in total, whereas in the OSI model, we say that it actually operates between the data link layer and the physical layer. And this is because it wasn't designed specifically for the OSI model, it was designed for the TCP/IP model. Now, ARP and RARP play very important roles in the way networks operate. If a computer wants to communicate with any other computer within the local area network, the MAC address is the identifier that's used. And if that device wishes to communicate outside of the local area network, the destination MAC address is going to be that of the router. So the ARP process works by first receiving the IP address from IP, or the Internet Protocol. Then ARP has the MAC address in its cached table. So the router has what are called ARP tables that link IP addresses to MAC addresses. We call this the ARP table. So it looks in there to see if it has a MAC address for the IP address listed. It then sends it back to the IP if it does have it, and if it doesn't have it, it broadcasts the message it's sent in order to resolve what we call resolve the address to a MAC address. And the target computer with the IP address responds to that broadcast message with what's called a unicast message, and we've discussed that contains the MAC address that it's seeking. ARP then will add the MAC address to its table, so the next time we don't have to go through this whole process. And then it returns the IP address to the requesting device as it would have if it just had it. Now, RARP is used to do the opposite. That is to map MAC addresses of a given system to their assigned IP addresses. And it sort of works in reverse from all this. Now, that's a very general overview of ARP and RARP, and if you were to go into Cisco certifications, for instance, you go a little more in depth into this. But for Network Plus, this is really where we need to stop with this protocol. So the next protocol I want to talk about is ICMP, which is also called the Internet Control Message Protocol. It's a protocol designed to send messages that relate to the status of a system. It's not meant to actually send data. So ICMP messages are used, generally speaking, for diagnostic and testing purposes. And they can also be used as a response to errors that occur in the normal operations of IP. And if you recall, one of the times that we talked about that was, for instance, with the MTU black hole, when that ICMP message couldn't get back to the original router. Now, many Internet Protocol utilities are actually derived from ICMP messages, such as Tracert or Traceroute, PathPing, and Ping. And we'll talk about these in a little more depth. And if you were around for A+, we definitely talked about these two quite a bit. ICMP is actually one of the core protocols of the IP suite, and it operates at the internet layer, which, as you recall, is TCP IP second layer. Now, ICMP is a control protocol used by networked computers and operating systems. And the most common utility that we're going to see is what's called ping, which we've talked about, which uses what are called ICMP echo requests. And they reply to determine connection statuses of a target system. So I could ping a specific system to see if it's on the network. Of course, there are some reasons why the ICMP, as we've talked about, might not make it back to me, or it's configured not to respond, perhaps through a firewall. Finally, we need to talk about IGMP, or the Internet Group Management Protocol. It should not be confused with ICMP. It's slightly different. It is used to establish memberships for multicast groups. Now, multicasting is where a computer wishes to send data to a lot of other computers through the internet by identifying which computers have subscribed or which ones wish to receive the data. We looked at this earlier and determined that routers determine a multicast group. Now, in a host implementation, a host is going to make a request for an IGMP implemented router to join the membership of a multicast group. Now, certain applications, such as those for online gaming, can use IGMP for what are called one-to-many communications. The one being the game server, and the many being all of those end users that have subscribed to the gaming session. So those routers with IGMP implementation periodically will send out queries to determine the multicast membership of those devices within range. And then those hosts that have membership are going to respond to the queries with a membership report. Now, the process of delivering an IP packet is simple. It begins with resolving the name of the host to its assigned IP address, like we talked about with RARP. And the connection is established by a service at, if you recall, the transport layer. Now, after the name resolution and connection establishment, the IP address is then sent down to the internet layer. And the next step is where the IP looks at the subnet mask, which we've talked about in A+, and we'll talk about more, of the IP address to determine whether the destination is local to the computer on what we say is the same subnet, or whether it's remote or on another network. After this determination is made, then finally the packet is routed and delivered. Okay, so we now understand TCP/IP a little more fully, some of the protocols that are dealt with in great detail, and how IP packet delivery works. So let's talk about binary and decimal, which are going to be really important when we get into what's called subnetting. And it's just good to know as an IT professional anyway. Specifically, understanding binary, or how to convert binary, which is the way computers talk, to decimal, which is the way that we deal with numbers, and decimal to binary, pertains to a lot of different aspects of, as I just mentioned, networking. So to begin with, binary, as the name implies from bi, is what we call a base 2 system. More commonly, we used a base 10 system, decimal. Now, this means that we have 10 possibilities for every place value. We have between 0 and 9. You add that up, there are 10. Now, with binary, there's only 2 options, either 0 or 1. So we can either have a single 0 or a single 1. And that's what we call a binary digit or a bit. So the binary number has place markers that are similar to the base 10 system. For instance, if we have a decimal base 10 numbering system, the second place mark designates the tens. If we imagine that there's a period or a decimal right there. The third designates the hundreds, and then we move to thousandths and 10,000ths and 100,000ths and so on and so forth. And in each one of these, we can have anywhere from 0 to 9, and that's 10 options in each one of those spots. Now, in a base 2 numbering system, which is binary, we have only 2 options, a 1 or a 0 in either one of those places. And in computers, especially in a lot of IP addressing, we really deal with the difference between 8 different places. So we're going to call these 8 an octet. So this 8-place binary digit is referred to as an octet because there's 1, 2, 3, 4, 5, 6, 7, 8 of them. And you'll see these numbers pop up over and over again. So this is really as far as you need to know for binary, although you can go even further. So if we look at this octet from the right side to the left, the first place mark is what we call 2 to the 0 power, right? If we were talking about this in tens, this would be the ones place. Why? Because it's 10 to the 0 power, which is ones. Anything taken to the 0 power is 1. Next, we have 10 to the first power, which is going to equal 2. If you recall, we call this the tens place. 10 to the 1 power means 10 by itself is 10. Then we have 10 to the second power, which is 4. And if you recall, in decimal, this is 10 to the second, which would be 10 times 10, which is 100. You can see where this is going. So 2 to the third is 8. 2 to the fourth equals 16. 2 to the fifth equals 32. 2 to the sixth equals 64. And 2 to the 7 equals 128. So each one of these place markers is equivalent to this number, whether it's turned on or off. Now, to help clarify this a bit, each place here has one of 2 options, correct? Because it's base 2. If it's off, that means it's a 0, as you see right here. And the number means it's not being counted, so we don't count any of these numbers we've just calculated. So if all the bits are off, that means that we have a number of 0. If all of the bits are on, then this means we add each of the numbers together. So we get 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which equals 255. Now, believe it or not, you can create any combination of numbers from just binary. You don't need decimal. And we're going to see that in just a second. So, for example, let's say the binary number is 000000111. Well, in this case, the 128, 64, 32, 16, and 8 bits are all off. The only ones that are on are 4, 2, and 1. And if we add those together, 4 plus 2 plus 1 will get 7. 4 plus 2 is 6, plus 1 is 7. If we take another number, say 011001110, then this is going to equate to 102. Why? 64 plus 32 equals 96, plus 4 equals 100, plus 2 equals 102. So it's pretty simple. You just take the number with the ones under it and add them together. So now that we've converted binary into decimal, a number that we all know, let's go ahead and see if we can convert the other way, decimal to binary. Now, for this process, we're going to use the same exact chart that we just saw with the binary conversion. And this chart is going to help us visually represent all the binary digits, which is why I like it, and they're placeholders, and it makes it a lot easier. So for decimal to binary, we simply go from left to right and break down the number until we reach the 0. So let me break that down a little bit. For instance, if we take the number 128, right, this is pretty easy to convert. We plug it into this chart. How many times does 128 go into 128? One time. If we take all the others and we subtract them, we're going to have 0, right? Because now 128 minus 128 is 0. That leaves us with our binary number 1000000, which is equivalent to 128. Now, if we take a look at a different number, let's say the number 218, this is going to take a little more math. Does 128 go into 218? It certainly does. So 218 minus 128 has a remainder of a certain amount, which is 90. Does 64 go into 90? It does. We now have a remainder of 26. Does 32 go into 26? No, it doesn't, so we put a 0. Does 16 go into 26? Yep, it does, which leaves us with a remainder of 10. Does 8 go into 10? It does, which leaves us a remainder of 2. Does 4 go into 2? It does not, so that leaves us with 0. We still have our 2. Does 2 go into 2? Yep. And then do we have anything left over? Nope, we're at 0 now, so we have 0. If we now add all those up, this is our binary number 110111010. Now, while this might seem like a fairly long process, it's important to understand how this works, because when we get into subnetting, it's really going to become important so we can have a better understanding of networking in general. So, just to recap everything we've talked about, we described these protocols in the TCP/IP suite. First, TCP, Transmission Control, and IP, Internet Protocol. One is connection-oriented, and the other is connection-less, meaning that it just is worried about delivery. Remember, IP is what is responsible for that IP addressing. UDP is also connection-less, similar in some ways to TCP, but it's not connection-oriented. Then we had ARP and reverse ARP, Address Resolution Protocol, which job is to map IP addresses to MAC addresses. We talked about ICMP, which is what we use when we're dealing with the status of a system. Internet Control Message Protocol. And then we talk about IGMP, the Internet Group Management Protocol, which is more dealing with multicast groups. We then talked very briefly about the IP packet delivery process, which was pretty simple, right? It's packaged, it's sent, we determine where it needs to go. Once it's determined where it needs to go, it's sent there. Finally, we explained the binary conversion, which is going to be really important for IP addressing, including how to go from binary, which is a base 2 system, to decimal, which is a base 10 system, and back again. Common network ports and protocols. All right, now we start getting into what I think is the fun stuff in this Network Plus exam. And in some ways, it's also where a good bulk of the questions are going to come from. By the end of this module, you're going to be able to say what each of these numbers represents in terms of a protocol. Now, if you took the A+ exam, and I hope you did, you probably recall some of these from there. So this might be a bit of a recap for you. But that's okay. It never hurts to go over this stuff again, especially because it just always pops up on the exam. And as far as knowing stuff, this is one of those things that you just have to know. These protocols are what you really have to know. And we're going to talk about the protocols in more depth later, too, when we talk about what TCP/IP is. But I want to start talking about these now, since a port is really the end point, logically, of a connection. So we're going to start by talking about what a port is in a little more detail and outline the different port ranges. There are 3 of them: well-known ports, registered ports, and then the last range, which is experimental sort of ports and private ports. So we're going to outline the most common, well-known default ports and the protocols that go along with them. I'm actually going to give you a huge list of all the protocols you need to know, and we're going to talk about some of those in depth in this module, some in the next module, and then some later on in the course. But I'm going to get them all out onto a chart for you right now. Finally, I want to define and describe the common ports and protocols dealing with FTP, or the File Transfer Protocol, NTP, or the Network Time Protocol, SMTP, the Simple Mail Transfer Protocol, POP3, or the Post Office Protocol, used to receive email as opposed to SMTP, which is used to send email, IMAP, which is also used for receiving or accessing email, which stands for the Internet Message Access Protocol, NNTP, or the Network News Transfer Protocol, something you may have used if you've ever used RSS feeds, HTTP, or the Hypertext Transfer Protocol, and HTTPS, which is the secure version. These are what allow you to browse on the internet. And finally, we'll talk about RDP, or the Remote Desktop Protocol, which allows you to remote in to a Microsoft computer. All right, so let's talk about these in more depth. First off, we have to define a port. In computers and networking, a port is a process-specific or application-specific designation that serves as a communication endpoint in the computer's operating system, meaning where the communication logically ends once it reaches the user. The port identifies specific processes and applications and denotes the path that they take through the network. Now, the Internet Assigned Numbers Authority, or the IANA, is the governing entity that regulates all of these port assignments and also defines the numbers or the numbering convention that they're given. Now, these ports range from 1 to over 65,000. Port 0 is reserved and it's never used, so don't really worry about that. Now, within this range, we actually have 3 different subsets of ranges. And as administrators, knowing the common ports is crucial to managing a successful network. The common ports are some of the guaranteed few questions that I know you're going to have on the Network Plus examination, and nearly every other network examination as well. So covering these and committing these to memory is of the utmost importance. Now, within that range from 1 to over 65,000, there are 3 recognized blocks or subsets of ports. The first block is considered the well-known ports. These ports range from 1 to 1023. This is where we're mostly going to look at ports when we look at them in just a minute. These are used by common services and are pretty much known by just about everyone in the field. Now, the next range of ports is called the registered ports range. These span from 1024 to 49,151. These are reserved by applications and programs that register with the IANA. An example might be, for instance, Skype, which registers and utilizes port, I think, 23399 as its default protocol. Don't worry about that, but if you're curious for your firewall's sake, this is the port I believe Skype uses. Finally, we have the dynamic or the private port range. This is everything else, 49,152 to 65,535. These are used by unregistered services in test settings and also for temporary connections. You can't register these with the INA. They're just left open for anyone to use for whatever purposes you may need them. So now let's talk about the well-known default ports you need to know for the exam. This chart is really what you should commit to memory, since and when you get to the test, you want to be able to basically recreate this chart before you sit down and take the test. You'll be able to do this on what's called a brain dump sheet. So let's talk about the first portion of these ports we need to know. The first is port 7. This is for the ICMP echo request, or ping. If you've ever pinged something from the command line, this is what we're talking about. We'll talk more about this a little bit later. Next, we have port 20 and 21. These are for the FTP or File Transfer Protocol, which allows you to transfer files over a network. We'll talk more about this in just a minute. Port 22 is for the Secure Shell or SSH, and port 23 is for Telnet. Both of those we're going to discuss later on in a different module, but they're sort of allowing you to remote in and control a remote computer, albeit not from a graphical standpoint. Port 25 is the SMTP or Simple Mail Transfer Protocol, which allows you to receive email, and DNS, or the Domain Name Service, which uses port 53, is what allows you to transmit or to translate, say, google.com into its IP address when you're browsing out on the internet. This is a really important protocol, and we'll talk more about it later, along with the DNS sort of server. Ports 67 and 68 are for what are called DHCP and BootP, or the Bootstrap service for servers and client respectively. One for servers and one for clients, as we can see right here. We're going to define and describe those in more detail in the next lesson. Now, port 69 is the Trivial File Transfer Protocol. This is related to the file transfer protocol we mentioned up here, but it is trivial, meaning that it is not connection-oriented and doesn't really guarantee that the file has been transferred. Port 123 is the Network Time Protocol, which keeps the clock on a network or on computers on the network up to sync. A great way to remember this is that time is always counting. 1, 2, 3. Port 110 is for the POP3 or the Post Office Protocol, which is how many of us download our email onto our local device. And then port 137 is the NetBIOS naming service. This is similar to DNS, but is specific to Windows operating systems or Microsoft operating systems. Related to POP3 is port 143, which is IMAP, the Internet Message Access Protocol. This is another way of accessing and managing your email. Let's continue taking a look at a few more protocols that are equally important. The first is the Simple Network Management Protocol, which allows you to manage devices on a network, say by getting error messages from your printer or from a router. This uses port 161. We'll discuss this a lot more in detail later as well. Port 389 is the Lightweight Directory Access Protocol. This is what allows a Windows server to have usernames and passwords. Port 443 is HTTPS, or the Hypertext Transfer Protocol over Secure Socket Layer. Notice the S here. This is what allows us to browse the internet, but securely. We also have port 500, which is IPSec. This one also has another name, which stands for Internet Security Association and Key Management Protocol. Basically, IPSec, or IP security, is what allows us to have secure connections over IP. Finally, we're going into RDP, or the Remote Desktop Protocol, which allows us to remotely access a computer, Windows-based specifically. Port 119, or the Network News Transfer Protocol, which is not only used with Usenet, a sort of message board that's been around for a very long time, but also RSS feeds, which you might be more familiar with. And finally, port 80 is HTTP, or Hypertext Transfer Protocol. The other thing to know about HTTP is it has an alternate port of 8080, so you might see either one of these on there. All right, now I know that was a lot of information I just threw out there, but we're going to cover these all in a little more depth as we go through here, and I just wanted to lay them out in a very simple chart-based way so that you could commit them to memory. Now let's talk about these in a little more depth, understand how they function, and why. First up is the File Transfer Protocol, or FTP. This protocol enables the transfer of files between a user's computer and a remote host. Using the File Transfer Protocol, or FTP, you can view, change, search for, upload, or download files. Now, while this sounds really great as a way to access files remotely, it has a few considerations that need to be kept in mind. The first is that FTP by itself is very unsecure, and an FTP daemon, which is a Unix term for a service, has to be running on the remote computer in order for this to work. You might also have to have an FTP utility or client on the client computer in order for you to have this protocol operate effectively and for you to be able to use it. Now, trivial FTP is the simple version of FTP and does not support error correction and doesn't guarantee that a file is actually getting where it needs to. It's typically not really used in many actual file transfer settings. Now, just as I just mentioned, you might need a client FTP software on your computer. Generally speaking, there is a command line prompt that you can use. It goes like this: FTP space the fully qualified domain name, for instance, google.com/FTP, which I don't think is the actual one, or the IP address of the remote host. You only need one or the other. If you provide the IP address, you're sort of using the direct route. If you're using what's called the fully qualified domain name, which we'll talk about a little bit later, then you allow something called DNS, or the Domain Name Service, to do the translation into a IP address for you. Remember again that FTP uses ports 20 and 21 by default. Next is the Simple Mail Transfer Protocol, or SMTP. This is used to manage the formatting and sending of email messages. Specifically, we're looking here at outgoing email. Using a method called store and forward, SMTP can hold on to a message until the recipient comes online. This is why it's used over unreliable wide area network links. Once the device comes online, it hands the message off to the server. The SMTP message has several things, including a header that contains source information as to where it's coming from, and it also has destination information as to where it's going. Of course, there's also content information, which is inside of the packet. The default port for SMTP is port 25, although sometimes you might see it use port 587, which is by relay. I wouldn't worry too much about that one for the exam, but just keep in mind port 25. Now, like SMTP, POP3 is a protocol that's used in handling email messages. And POP3 stands for the Post Office Protocol, version 3, which is the commonly used version now. Specifically, POP3 is used for the receipt of email or incoming email. And it does this by retrieving email messages from a mail server. It's designed to pull the messages down, and then, once it does that, the server deletes the message on the server source by default, although you can change that if an administrator wants to. This makes POP3 not as desirable and weaker than some other mail protocols, specifically IMAP, which we're going to see, because it puts all of the brunt of the responsibility onto the client for storing and managing emails and deletes all the emails at the source. So if something happens to your computer and you don't have a backup, you're in big trouble. The default port for POP3, as we mentioned, is port 110. So remember, port 110 is POP3, and port 25 is SMTP. Now, IMAP4, usually just called IMAP, is the Internet Message Access Protocol. And it's similar to POP3 in that it's also utilized for incoming mail or mail retrieval. But in nearly every way, IMAP surpasses POP3. It's a much more powerful protocol because it offers more benefits like easier mailbox management, more granular search capabilities, and so on. With IMAP, users can search through messages by keywords and choose which messages they want to download. They can also leave IMAP messages on the server and still work with them as though they're on the local computer. So it seems that the two are synced together perfectly, the server and the client. Also, an email message with, say, a multimedia file can be partially downloaded to save bandwidth. Now, the main benefit here is we're going to use this instead of for, say, a computer. Let's say I have a smartphone and a computer. Now, it's going to make sure, because the source is all stored at the server, that if I delete something, say, on my computer, that syncs up to the server, and then the server will have that sync with my smartphone. So all of these are in perfect synchronization. This is why it's much stronger than POP3, which simply downloads the email onto your client device. By default, IMAP uses port 143, which is different from IMAP, POP3 rather, which uses 110. Now, NTP, or the Network Time Protocol, is an internet protocol that synchronizes system clocks by exchanging time signals between a client and a master clock server. The computers are constantly running this in the background, and this protocol will send requests to the server to obtain accurate time updates up to the millisecond. This time is checked against the U.S. Naval Observatory master clock or atomic clock. So the timestamps on the received updates are verified with this master clock server, which is again that U.S. Naval server. And the computers then update their time accordingly. The port this uses is port 123, which is as easy to remember as time keeps moving up. 1, 2, 3. Now, if we add an additional N to the previous one, we get what's called the Network News Transfer Protocol. This is very different from the Network Time Protocol. It's used for the retrieval and posting of news group messages or bulletin messages to the Usenet, which is a worldwide bulletin board that's been around since the 1980s, really since the internet was in its nascent stages. The Network News Transfer Protocol is also the protocol that RSS feeds are based on. This stands for Really Simple Syndication. Basically, this is where a user can subscribe to an article, web page, blog, or something similar that uses this protocol. And when an update is made to that page or to that article, the subscriber is updated. So in this way, you can get updated articles from your favorite web page just like you would new emails. With NNTP, however, only postings and articles that are new or updated are submitted and retrieved from the server. Slightly different from RSS, but RSS is based on NNTP. The default port for this is port 119. So, we're covering a lot of different numbers here. It's really important, perhaps even more than memorizing specifically what each protocol does, that you definitely memorize which port it's a part of. If you can memorize, by the way, the number and what the acronym means, you should be fine. Now, a protocol you use every day, even if you don't realize it, is HTTP, or the Hypertext Transfer Protocol. This is used to view unsecure web pages and allows users to connect to and communicate with web servers. Although HTTP is going to define the transmission and the format of messages and the actions taken by web servers when users interact with it, HTTP is what we call a stateless protocol, meaning that it may be difficult to get a lot of intelligent, interactive responses to the information. If you remember ever making very basic web pages using HTML or the hypertext markup language, the language that HTTP is reading, then you probably know this. So if you want more interactive web pages or interaction with web pages, then you're going to use different add-ons, such as ActiveX that you might have heard of. HTTP defaults port is port 80, and a common alternate port for it is port 8080. Now, similar to HTTP is HTTPS, or Hypertext Transfer Protocol over SSL, which is the Secure Socket Layer. This is a secure version of HTTP. So if you ever see an S on the end of just about any protocol, you can bet that that has to do with this, being secure. And it creates secure connections between your browser and the web server. It does this using SSL, or the Secure Sockets Layer. We're going to discuss the Secure Sockets Layer when we discuss encryption in more detail in a future lesson. Now, most web pages support HTTPS, and it's recommended that you use it over HTTP almost every time you're able to. The way you do this is simply by using, instead of http://facebook.com, just put an S in front. Yes, Facebook supports this, as do other social media sites, and even email, and even Google supports HTTPS. Why would you want to do this? Well, say someone is browsing or listening in to your Google searches. That might be information you don't want someone else to know. Just as a recommendation, absolutely anytime you visit any website, but especially financial institutions such as your bank or your credit union, you want to ensure that in the bar it says HTTPS. If it's not, then opening anything in this, including typing in your bank password, could be really serious. The same goes for anything when we're dealing with credit cards, for instance, buying something. Make sure that HTTPS appears in the bar or in your URL bar at the top. As we've mentioned before, too, the default port is port 443. Now, the last port I want to discuss is RDP, or the Remote Desktop Protocol. RDP servers are built into the Microsoft operating system, such as Windows, by default. And it provides users with a graphical user interface, or a GUI, to another computer over a network connection. So this protocol allows users to remotely manage, administer, and access network resources from another physical location over the internet, which is represented by the cloud. There are a few security concerns that come with RDP, and there is potential for certain sort of computer attacks. So there are also non-Microsoft variations available, such as something called RDesktop for Unix, which if you are going to be doing a lot of remoting, you might want to look into. RDP, by the way, uses default port 3389, although you can change that. Usually as well, when we're using RDP, we're also going to use it over what's called a VPN, or virtual private network, which creates a tunnel through which your connection occurs. This improves the security we were just talking about. So let's review what we've just talked about. First, we talked about a port being the logical endpoint of a connection, and then we outlined the port ranges. Remember, we had the well-known ports, the registered ports, and then the dynamic or private or experimental ports. What we really want to learn for ourselves are the well-known ports. I then outlined the most common well-known default ports and their protocols. You want to memorize this table for the Network Plus exam. I guarantee you doing that will get you a bunch of questions on the exam. Finally, we defined and described some of the specific ports, and we looked not only at the protocol and their protocols, including FTP, or the File Transfer Protocol, NTP, or the Network Time Protocol, SMTP, or the Simple Mail Transfer Protocol, POP3, or the Post Office Protocol. We also looked at IMAP, the Internet Message Access Protocol. And again, all three of these have to do with email. We also looked at an NTP, which is not Network Time Protocol, but the Network News Transfer Protocol. We looked at two different versions of HTTP, one that is secure. These allow for browsing, and it stands for the Hypertext Transfer Protocol, which, if you know HTML or the Hypertext Markup Language, then that might be familiar to you. And finally, we looked at RDP, or the Remote Desktop Protocol. I know this seems like a lot, but I guarantee memorizing all of these and all of the numbers that they're associated with is going to help you so much on the exam. Interoperability services. This word interoperability is a really long one, but it's also a good one. Basically, what this means is how different types of operating systems and computers can communicate with one another over a similar network. And that's what we're going to be discussing in this module. So we're going to first cover what interoperability services are in a little more depth. Then we're going to define some specific services that qualify as these, particularly NFS, or the Network File System. I'm sure you can imagine what that is from its name. We're also going to look at SSH, which is the Secure Shell, and SCP, Secure Copy Protocol. Remember, every time we see that S, we want to think security. That's a great tip that'll help you out on the test. By the way, Secure Copy Protocol is similar to SFTP, or the Secure File Transfer Protocol. We're then going to look at Telnet, or the Telecommunications Network, and SMB, or the Server Messenger Block, which is what allows us to share, for instance, files and printers. We're also going to look at LDAP, or Lightweight Directory Access Protocol, and that word directory is important as it allows us to manage users in our network. And then ZeroConf in networking, which also stands for Zero Configuration Networking, a set of protocols that allows us to sort of plug in and go without having to do a lot of advanced configuration and setup. This is what allows us to have very easy plug-and-play network devices such as our SOHO routers, which is a good way to think about it. However, it's also deployed in much larger operations in order to ease the burden on administrators and technicians. So, in the previous module, we discussed several different protocols that were used in the TCP/IP protocol suite. And these allowed us to do a lot of different things. By the way, TCP/IP, which is what basically allows us to communicate over the network in general, is going to be discussed in more detail and depth later on in this course. Now, because not all computers are made the same or by the same people or individuals, certain protocols and services need to be in place to allow dissimilar systems, such as PCs and Macs, to be able to interact with one another. So TCP/IP also contains these interoperability services that allow dissimilar services or systems to share resources and communicate efficiently and securely, which is important if I want to make sure that no one is reading all of the information I'm sending between computers. So these services is what we're going to spend the rest of this module discussing. Now, the first service is the Network File System. It's an application that allows users to remotely access resources and files, a resource being, for instance, a printer, and a file being like a Word document, as though they were located on a local machine, even though they're someplace else. This service is used for systems that are typically not the same, such as Unix, which is the larger version or the commercial version of Linux and Microsoft systems. Now, NFS functions independently of the operating system, the computer system it's installed on, and the network architecture. This means that NFS is going to perform its functions regardless of where it's installed. And since it's what we call an open standard, it allows anyone to implement it. It also listens on port 2049 by default, but I wouldn't worry about memorizing that for the test. Next, SSH, or the Secure Shell, is one of the preferred session-initiating programs that allows us to connect to a remote computer. It creates a secure connection by using strong authentication mechanisms, and it lets users log on to remote computers with different systems, independent of the type of system you're currently on. With SSH, the Secure Shell, the entire connection is encrypted, including the password and the login session. It's all compatible with a lot of different systems, including Linux, Macs, and PCs, and so on. Now, there are actually two different versions of Secure Shell, SSH1 and SSH2. These two versions are not compatible with one another, which is important to know, because they each encrypt different parts of the data packet, and they employ different types of encryption methods, which we'll talk about later. However, the most important thing to know is that SSH2 is more secure than SSH1, and so in most cases we want to use that. This is because it does not use server keys, SSH1 doesn't, which are keys that are temporary and protect other aspects of the encryption process. It's a bit complex and over the objectives of this course. However, SSH2 does contain another protocol called SFTP. And SFTP, or the Secure File Transfer Protocol, is a secure replacement for the unsecure version of plain old FTP. And it still uses the same port as SSH, which, if you recall, is port 22. So it's important to know that if we're going to be using SFTP, remember FTP uses 20 and 21. If we're using SFTP, we're using port 22. Now, similar to SFTP is SCP, or the Secure Copy Protocol, which is a secure method of copying files between remote devices, just like FTP or SFTP. It utilizes the same port as SSH, just like SFTP, and it's compatible with a lot of different operating systems. To implement SCP, you can initiate it via a command line utility that uses either SCP or SFTP to perform some secure copying. The important thing here to know for the Network Plus exam is not when you would use SCP over SFTP, which is a little bit more complex, but rather to realize that SCP is a secure method of copying, as is SFTP. That's how you're going to see this pop up on the exam. Now, in contrast to all of this secure communications, I want to talk about Telnet, or the Telecommunications Network, which is a terminal emulations protocol. What this means is that it's only simulating a session on the machine it is being initiated on. When you connect to a machine via a terminal by using Telnet, the machine is translating your keystrokes into instructions that the remote device understands, and it displays those instructions and the responses back to you in a graphical or command line manner. Telnet is an unsecure protocol, which is why we don't use it as much as SSH anymore. And this is important to keep in mind. So when you send the password over Telnet, it's actually in what we call plain text. Whereas, as we mentioned with SSH, it transmits the password encrypted. So if someone is reading the packets that are going back and forth, they won't be able to hack your system if you're using SSH, whereas with Telnet, they'd be able to read your password. Now, Telnet uses port 23 by default, which is important to know. However, you could configure it to use another port as long as the remote machine is also configured to use that same port. With Telnet, you can actually connect to any host that's running the Telnet service or daemon, which again, the word daemon is a Unix version of service. SMB, or the server message block, which by the way is also known as CIFS, or the Common Internet File System, is a protocol that's mainly used to provide shared access to files, peripheral devices like printers most of the time, and also access to serial ports and other communication between nodes on a network. Windows systems used SMB primarily before the introduction of something called Active Directories, which we'll talk more about a little bit later. This is currently what's used in Microsoft networks. Now, Windows services that correspond are called server services for the server component and workstation services for the client component. Now, for example, the primary functionality that SMB is typically most known for is when client computers want to access files, systems, or printers on a shared network or a server. This is when SMB is most often used. Samba, which you may have seen if you've ever dealt with a Mac or a Linux computer, is free software that's a re-implementation of the SMB or CIFS networking protocol for other systems. Even though SMB is primarily used or was primarily used with Microsoft systems, there are still other products that use SMB for file sharing in different operating systems, which is why it's important that we still familiarize ourselves with it. LDAP stands for the Lightweight Directory Access Protocol. And this is what defines how a user can access files, resources, or share directory data and perform operations on a server in a TCP IP network. Now, this is not how they access it. This simply defines how a user can access it, meaning that what we're really talking about here are users and permissions. So basically, LDAP is the protocol that controls how users manage directory information, such as data about users, devices, permissions, searching, and other tasks in most networks. We're going to deal with this a little more in depth later on as well. Now, it was designed to be used on the internet, and it relies heavily on DNS, the domain name service, which we talked about is a way of converting, say, google.com into its IP address. We're going to discuss DNS in greater detail in another module. Now, Microsoft's Active Directory service, which we just mentioned, and Novell's NDS and eDirectory services, Novell being another networking operating system, as well as Apple's Open Directory directory system, all use LDAP. Now, the reason it's called lightweight is because it was not as network intensive as its predecessor, which was simply the Directory Access Protocol. No need to know that, but I just wanted to explain the reasoning behind that lightweight in there. Also, it's important to know that port 389 is used by default for all the communication of the requests for information and objects. Finally, zero-conf or zero configuration networking is a set of standards that was established to allow users the ability to have network connectivity out of the box, or plug and play, or without the need for any sort of technical change or configuration. Zero-conf capable protocols will generally use MAC addresses, or the physical addresses, as they are unique to each device with a NIC, or network interface card. In order for devices to fit into a zero-conf standard, they have to fit or meet 4 qualifications or functions. First, the network address assignment must be automatic. if you recall from A+, and this is something we'll talk about a little later, this is what we use when we're using DHCP. Second, automatic multicast address assignment must be implemented, which is also related to the DHCP standard. Third, automatic translation between network names and addresses must exist. This is what we talk about when we deal with DNS. Finally, discovery of network services or the location by the protocol and the name is required, meaning that it must be able to find all of this information when it goes on the network automatically. This is what allows users to be able to purchase a router from the local Best Buy or electronics store, take it home, plug it into their ISP or internet service provider connection, and automatically have it work automatically. Another implementation, by the way, of this is a configuration in networking called UPnP, or Universal Plug and Play. So to recap what we've talked about, we talked about interoperability services, which allows, for instance, a PC and a Mac to communicate flawlessly over a network. We then talked about the network file service, SSH and SCP, SSH being a secure shell working on port 22, and SCP being the secure copy protocol, similar to SFTP, the secure file transfer protocol. We looked at Telnet, which is sort of a plain text version of SSH, so it's been replaced by it, and SMB, or the server message block, allowing us to share files and resources between different types of systems. Finally, we described and defined LDAP, or the Lightweight Directory Access Protocol, which defines users and their ability to access all this stuff on the network. And then we explained ZeroConf, or zero configuration in networking, which allows us to plug up a device and have it work almost instantaneously. IP addresses and subnetting. So having discussed IP addressing and routing in general, we're now going to further examine IP addressing and the methods of logically, not physically, dividing up our networks. This way, we can keep not only better track of all the devices on the network, but also organize them for security, performance, and other reasons. After we complete this module, we're going to have a better understanding of how our network devices are identified, both by other devices and by individuals such as ourselves, since we're not computers. So first, we're going to identify what a network address is versus a network name. One, the network address is for other devices. A network name is really for us, since it would be difficult for us to remember all these numbers, much like using a phone number in a cell phone. Next, we're going to describe the IPv4 addressing scheme. And IPv4 is important to know because even though we have a newer version, IPv6, IPv4 is still deployed in most situations, and it's covered to the most extent on Network Plus. When we get to IPv6, which is different, version 6, there are a lot of benefits to that, and we'll describe it later, but really understanding IPv4 is really important. After we take a look at that, we're going to look at subnetting and a subnet mask. You might have seen this, and these are the numbers, and we've probably mentioned them in the past, such as 255.255.0.0, and so on and so forth. And we're going to describe how this allows us to separate out the network ID from the node ID, or the device's ID or address from the network's address, much like our zip code versus our street address. After that, we're going to describe the rules of subnet masks and their IP addresses, and knowing binary is really going to help us understand all of this stuff. After that, we're going to apply a subnet mask to an IP address using something called ANDing, which again gets back to binary, and might even remind you of something you learned in high school, this ANDing principle, which is really going to come in handy. And again, this is something that we only have to do now with IPv4. IPv6 doesn't have to do it, and we'll describe why. Finally, we're going to take a look at what are called custom subnet masks, which are slightly different from these default ones, the 255.255.255s, and so on. So, having said all that, let's get into it by looking at network addresses and names. So let's begin by looking at how nodes on a network are identified, specifically on the internet or network layer. If you recall, the network layer is layer 3 of the OSI model, and the internet layer is layer 2 of the TCP IP model. So to begin, a network address is assigned to every device, and I think we've discussed this, that wants to communicate on a computer network. The network address is actually made up of two parts. The node portion that belongs to the specific device, and the network portion, which identifies what network the device belongs to. I think I've just described this as a zip code, which describes the sort of network or the area you're in, versus your street number and your street address, which is specific to where you live. This address is what is used by devices for identification, and as it's only made up of numbers, whereas a network name is made up of letters and such, the real reason being readability. We would have a lot of trouble remembering. We already have trouble remembering a phone number, but if you imagine remembering a whole binary number or a set of numbers where there's infinite possibilities, unless you're using it a lot, it's easier to remember a name, such as the conference room laptop or resource server 1, than it is to remember an IP address, which might be something like 132.168.56.43. Especially when there are a lot more computers involved, the names become a lot easier. So the network named is actually mapped to the address or the IP address by one or another naming services, and some of these we've discussed. Now, as devices only communicate with each other by their network address, the naming services are really crucial to the operation of a network. There are 3 different network services used that you should be aware of. The first, DNS, which we've mentioned before, also called the Domain Name Service, is a naming service that's used on the internet in most networks. It's what allows, for instance, you to type in google.com, which we would call a fully qualified domain name, and it will translate that to the IP address of Google, whatever that might be. The next naming service is Windows specific, and it's called WINS, or the Windows Internet Naming Service. It's really outdated, and it was used on Windows networks. The only reason I mention it is you might see it mentioned in a test question, and it might help you. But you're really not going to see it used in the field much anymore. And finally, we have one called NetBIOS, which is a broadcast type of service that has a maximum length of 15 characters. And it was used, or still is used to a certain extent, on Windows networks as well. A good understanding of all of these network identification aspects, addresses, and names is important at this very fundamental level. So now that we sort of have a general overview of these, let's take a look at some of the specific type of network addressing, specifically IP version 4. Now, IPv4, IP version 4 addresses is a very important aspect of networking for any administrator or technician or even just IT guy to understand. It is a 32-bit binary address that's used to identify and differentiate nodes on a network. In other words, it is your address on the network or your social security number. With the IPv4 addressing scheme being a 32-bit address, and you can see if we counted each one of these up, remember a bit is either a 0 or a 1, and we can count up there are 32 of these. This means that there are theoretically up to 4.29 billion addresses available. Now, that might not sound like we're ever going to hit that, but in fact, we've already gotten there. And so part of the problem is, how do we share 4.29 billion devices with 4.29 billion addresses with even more billions of devices in the world? So this 32-bit address, which is why we've had to develop another one called IPv6. But anyway, I digress. The 32-bit address is broken up into 4 octets. This makes it easier for people to remember and to read. And you can see those here. And if you've ever seen like a 192.168.0.1, those are the 4 octets. This system and structure of these address schemes is governed and managed by 2 standard organizations. One is called the IANA, which stands for the Internet Assigned Numbers Authority, and the other is called the RIR, or the Regional Internet Registry. I wouldn't worry about memorizing these, I'm just mentioning them so you know sort of who's coming up with all this stuff. Now, every device on the network is going to have its own unique address. So there are 2 types of addresses in general. One is called class-full, and these are default addresses, and the other are called classless, which are custom addresses. We're going to talk about the classless ones in a later module, and we're going to define both of these in greater detail a little bit later on. As a network address, it's also made up of 2 parts: the network portion and the node portion. Let me just erase all this writing here so you can see exactly what I mean. In order to tell, now in this section, you can see the network portion are the first 2 octets, and the node portion are the last 2 octets. But that is not always the case. In fact, if we were to just take those away for a second, and this is how the computer looks at them, we can't actually tell which is which. And that's why we need something called a subnet mask. The subnet mask allows us to determine which is the network portion and which is the node portion. That way, we know, for instance, where the area code of the phone number begins and the rest of the number ends. So the network portion would be like the area code of your phone number, or the international code. It tells you which network that is on. The node portion tells you exactly which phone on that network we're going to try reaching out to. So we're going to further logically, again, not physically, divide a network into smaller subnetworks called subnets. Now, this logical division is beneficial because of 3 reasons. 1, it can effectively increase the efficiency in packet routing, because if I know that my information is destined for a specific network, I don't have to bother with asking, let's say, 5,000 or 5 million or 5 billion computers if I'm meant for them. I can go directly to the network where I want to go, just like with area codes and phone numbers. The next is it allows for better management of multiple networks within a single organization. For instance, if I'm a network administrator, it might be easier to have separate subnets so I can organize who's on which subnet, so that way not only are things going to be routed more efficiently for that person, but it's easier for me to manage on paper and in my administrative duties. And finally, it potentially offers a certain level of security, since I'm only going to be able to access easily information that's on the same network or subnetwork that I'm on. Now, a subnetted IPv4 address is actually comprised of 3 different parts: the net ID, the host ID, and the subnet ID. Now, if a device on a subnetted TCP/IP network wants to communicate, it's going to need to be configured with an IP address and a subnet mask. And we'll look at these in just a second. The subnet mask is what is used to identify the subnet that each node belongs to. This also allows us to determine which network it's on. Connectivity devices such as routers or upper layer switches, and we're talking about layer 3 devices here, and remember, layer 3 devices look at IP addresses, not just MAC addresses, are used on the borders of these networks to manage the data passage between and within the network. That's how we're going to get better routing efficiency, easier management, and potentially make it more secure. Because if I have any one network and I have let's say a switch, we'll put this as switch, and it has 4 computers on it, and then I have another switch, and these are layer 2 switches, okay? And each of these, let's say we have our different subnets, then I'm going to divide these up by a router, which now is going to make sure that data that's going here kind of gets bounced back unless it's meant for this guy. And this way we're really reducing the traffic on it. Now a subnet mask is, like an IP address, a 32-bit binary address broken up into 4 octets in a dotted decimal format, just like an IP address. And it's used to separate the network portion from the node portion. And I'm going to show you how that works in just a minute, and it involves a little bit of knowledge of binary, which we've already talked about. So the subnet mask, and that name mask sort of lets you think of it as being put onto the IP address, is applied to that IP address and removes the node ID. The subnet mask therefore eliminates or removes an entire octet of the IP address by using 8 binary ones, or 255 in decimal format, meaning that this 255, if we add it up in binary, would be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then this would be 1, 2, 3, 4, 5, 6, 7, 8. So meaning that a 255 equals 8 ones, which is the reason why an IP address can never be 255. And if this is a little confusing, that's okay. We're about to clarify that in just a second. So IP addresses, IP address assignments, and subnet masks all have to follow a certain set of rules. I'm going to describe the rules and then I'm going to apply them. So if some of this is a little confusing or over your head, keep paying attention, keep with me, and I think it's going to clarify itself. The first is that the ones in a subnet mask will always start at the left, meaning the first octet will always be 255 or 8 binary ones. So my subnet mask, I'm always going to start at the left when I'm writing it out. This says that the first octet is going to be 255, which means 8 bits. Now the zeros of the mask will always start at the 1 bit, or all the way on the right, meaning that I'm going to have zeros from the right and ones from the left. And the ones in the mask have to be adjoining or consistent or continuous or contiguous, whichever word you want to use, meaning once there is a 0, we cannot then go back to ones. So we're not going to see like this sort of thing happen. In fact, we have to have continuous ones from the left and continuous zeros from the right. This is the only way a subnet mask is going to work. And I'll talk about why in just a minute. Also, if there is more than one subnet on a network, every subnet has to have a unique network ID. And I'll explain this in a bit. But it makes sense. If I have different network IDs, then I'm not really, if I have similar network IDs, then I'm not really dealing with multiple networks. I'm dealing with the same network. Now, assignment of IP addresses have to follow a few more rules. So these are the subnet masks. First, there cannot be any duplicate IP addresses on the network. This means that every network, every device has to have its own unique IP address. We cannot have more than one device with the same IP address. If we do, they're not going to be able to communicate because the switches won't know where to send packets. Next, if there are subnets, every node must be assigned to one of them, meaning that every address, every IP address has to be assigned to a specific network. Now, the address of a node cannot be all ones or all zeros. Remember, all ones would be 255. All zeros would be just 0.0.0.0. So I cannot have an IP address that is either 255.255.255 or that can be 0.0.0.0. And you'll see why when we get to the mathematics of this in just a second. It's because then I would never be able to determine a network ID from a node ID. Finally, and this is something you sort of have to remember, the IP address can never be 127.0.0.1. We talked about this in A+, but that's because this is what's called the loopback. It's a reserved IP address specifically for yourself. It'd be like saying me, myself, or I. I cannot have a 127.0.0.1 IP address assigned to a device because every device calls itself 127.0.0.1. Now, besides understanding these rules, which are a bit abstract, I think, we need to know how to apply them and how to apply a subnet mask to an IP address. I think it's going to make some of these rules a little clearer, so let's take a look at those. Now, when a subnet mask is applied to an IP address, the remainder is the network portion, meaning when we take the IP address and we apply the subnet mask, and I'll show you how to do that in a second, what we get as a remainder, what's left over, is going to be the network ID. This allows us to then determine what the node ID is. This will make more sense in just a minute. The way we do this is through something called ANDing. ANDing is a mathematics term. It really has to do with logic. The way it works is, and you just have to sort of remember these rules, 1 and 1 is 1. 1 and 0 is 0. And the trick there is that that 0 is there. 0 and 1 is 0, and 0 and 0 is also 0. So basically what ANDing does is allows us to hide certain certain bits from the rest of the network. And therefore we're allowed to get the IP address, or rather the network address, from the node address. So let's take a look at this for just a second. Let's say we have an IP address 162.85.120.27, and we have a subnet mask of 255.255.255.0. Now, let's take a look at how this works when we move it into binary. 162.85.120.127 equals this in binary. And if we wanted to write out these places again, if you remember, we had, this was a base 2, right? So these are the place settings. I'm just going to write these out real quickly, and then I'm going to erase it all. Okay? And so we get 1, 2, 4, 8, 16, 32, 64, 128. And it's good to sort of commit these to memory. Therefore, the reason this is 1, 1, 1 is we take that 128, we add it to 32, and we add it to the 2, because those are the bits that are on. And when we add 128 plus 32, we get 160 plus 2 gives us 162. So it works out, and you can see my math is correct here. I'm going to erase all this now. Try to remember this AND thing in here for a minute. Now, if we convert 255.255.255.0 into binary, we've already talked about this, we're going to get all these 1s. And then, because this is 0, we're going to get 0. Now, if we apply the ANDing principle, this is what we're going to get. Anything with 1 and 1 turns into a 1. Anytime we see a 1 and a 0, we're going to get a 0. And if we apply this out, here's what we get. Now, because we have all these zeros here, it's basically going to block all these 1s from coming down and coming through. Right? They all turn into 0. So, if we convert this back into a decimal, we now get 162.85.120.0. Basically, and this is pretty simple to see, we can see that the 162 drops down, the 85 drops down, the 120 drops down because of this ANDing that we just talked about, and the 27 gets blocked by these zeros. And so we can determine that the 162.85.120 is what we call the network ID. Now, by looking at it this way, we can see then that the network portion of the address is going to be the first 3 octets, as we just pointed out, and the node portion is going to be the last octet. So this is the first step in subnetting, and it tells us a lot of things about the networks. Just by knowing the IP address and the subnet mask, a technician can now discern a lot of things, such as what portion is the network ID, what portion is the node ID, and therefore what is my first usable IP address, and what's my last usable IP address that I could start to give to devices. I can also determine stuff like what we call the default gateway, which we'll look at in a second, and the broadcast address, which we'll also look at, not in a second, then in the next module. Now there are 3 default subnet masks, as you can imagine. And these have to do with what we call a classful IP addressing system, and we'll talk about that next, the next module. But the default subnet masks are 255.0.0.0. Just going to go with the class A, and we'll talk about that. 255.255.0.0 and 255.255.255.0. What you can see is, if you have a default subnet mask, then you know immediately, just by looking, what the network address is and what the node address is. As you can imagine, if I have this as my network address, I can have a lot of networks and only so many nodes. This one, I have more nodes, a little bit less networks, and on this one I have a lot of nodes but fewer networks to divide them up on. Now it would be great if all subnet masks were as simple as this. We wouldn't even really ever have to break it down into this binary sort of coding, because you could just look at it and say, oh, it's 255, I know they're all going to be ones, I know that's going to AND out, and therefore I know it's going to end up right here. But unfortunately, this is not always the case. Sometimes we have what are called custom subnet masks. Now, by using a custom subnet mask, we can actually further divide or subdivide our IP address, and in these cases, it can be a little more difficult, and so converting to binary is actually necessary to break it down. Custom subnet masks are created by what we call borrowing bits from the host portion to use to identify the subnet portion. So you can see we've just borrowed a bit, this one, right over here. Now, keeping in mind that the subnet mask rules allow us to borrow bits from the node portion and give them to the network portion, the bits from the left to the right of the portion, like this, are switched on. Now, turning this bit on means we now have different values for the subnet mask. Instead of just 255.255.255.0, we know this is no longer 0, right? So this is actually now going to be 128. And we can have a number of these, and if you keep adding over to the right, so 128, and then we added 64, we get 192, and so on and so forth. So we can actually have a number of custom subnet mask values in the last octet, and those are these. And so you can see, in this case, it's not really going to make much of a difference when I do all the binary bidding, because you see that the 0 and the 0 is still going to become a 0 here. And so all of this is really going to look the same, and so our network portion is actually going to look the same as it did before. We have the same network ID as we did before. But let's say that this was actually, this number, by the way, is the same as the one we had before, 162.85.120.27. If this was instead 128, we're going to have an issue, because this is going to be on. These would say let's be off. And when they come down, this is going to turn into a 0 as opposed to that 1 dropping down. And so it's going to change what our IP address in the end looks like. And so we actually need to do some backward engineering to get to our subnet mask. Now, this is all really complex, and when we get into, if you ever get into Cisco, you'd really have to know this. But for our purposes, you really don't need to know this that in depth. All right, so just to recap what we talked about here, we got a basic understanding of a lot of things, not too in depth, and you might need to rewatch this video to really get it, and maybe even do a little bit of exercises on your own. First, we talked about the difference between a network address and a network name. remembering that the three network name services that match a name, such as Bill's laptop, to an address, which would be something like 192.168.0.1, we can use either DNS, the domain name service, which is the most popular one, something called WINS, which is specific to Windows, or NetBIOS, also a Windows-based naming system. The one we want to be most familiar with is this. This one's not really used anymore. NetBIOS is still used in certain instances, especially in older networks. We then talked about the IP version 4 address and the things that it requires, including, and remember, a IPv4 address is that 32-bit broken up into 4 octets. The reason it's called an octet is because we have 8 times 4 gives us that 32, and we break it up. So, for instance, 192 is going to break down to a certain amount of bits. Okay? We also talked about defining subnetting and a subnet mask, which the most important thing it does is distinguishes our network from our node ID. In other words, what's our area code, and then what is our phone number. We can have the same phone number in different area codes, but they go to very different people. We also talked about the rules of subnet masks and IP addresses. We can only have one IP address on any network, and we can not use 127.0.0.1 because that is what we call the loop back address. As far as for the subnet mask, remember that all ones have to be continuous from the left and zeros have to be continuous from the right. Our defaults are 255.255.0.0.0 and then 255. I'm sorry, I think I just said 255.0.0.0, 255.255.0.0.0, and 255.255.255.0. Those are our defaults. And so we talked about applying a subnet mask using something called ANDing. And we looked at how that divides up, again, the network ID from the node ID, and we saw that in practice. Finally, we talked very briefly about custom subnet masks, something that we don't have to get very much into. But we talked about how if we had 255.255.255. For instance, 128, we could have these sort of subnets, or these, we could break it down even further. And therefore, we could start to do a lot more stuff. And in the next module, I'm going to talk about this in a lot more detail and why we would want to do it. Default and custom addressing. So we described in the previous module subnetting, how to determine the network from the node ID, and we talked specifically about IPv4, and we're going to continue talking about IPv4 a little bit more. First, by defining the default IPv4 addressing scheme. Now, some of this we sort of touched on in the previous module, and some of the stuff we're going to talk about right now is going to probably help clarify that. And so it might even help to go back and watch the previous module after watching this one. After that, we're going to talk about the reserved or restricted IPv4 addresses. One of the ones we've already mentioned is what we called the loopback, or 127.0.0.1. That's an example of a reserved IP address, or restricted IP address. And so we're going to talk about those in more depth, and some of the ones that, some of the ranges that are restricted, and why they are. Then we're going to discuss what are called the private addresses. And we're going to talk about these specifically because these are different from public IP addresses. One you might be familiar with is the 192.168 private addresses rather. And this is going to explain why every router that you purchase at electronics store has this as its default. Not everyone, but a lot of them have this as the default IP address, and yet we talked about how you can't have more than one IP address with any device. And so we're going to describe why with private IP addresses this is the case, and we'll talk about some other private IP addresses as well. Then we're going to talk about the IPv4 formulas, and that's what allows us to determine how many hosts and networks are permissible based on the type of IP address, the class that it's in, and the subnet mask that's applied. And this will help us also determine, and we'll talk about in a second, why we might want to use custom subnet masks and custom IP addresses. So then we're going to talk about what the default gateway is. This gets back to actually this right here. It is the device which any node needs to know in order to get out to the network and to the rest of the world. Finally, we're going to talk about custom IP address schemes, VLSM, and CIDR. These are a little more in depth, but these really get back to the subnet masks and why we can apply those, how we can apply sort of specific subnet masks to things. And we'll look at this thing, which you might have seen, CIDR, which has to do with why there might be a slash after an IP address, which really gets to the number of bits it has. And we'll talk about that in just a minute. Now, aside from being an aspect that's covered in many areas of the Network Plus exam, understanding the classes in a default IP address scheme is really important for us. And this gets back to right here. So let's talk about, remember we talked about classless and classful. We're going to talk about the classes that exist in an IP address right now. So as we learned in previous modules, the IPv4 addressing scheme is again 32 bits broken up into 4 octets. And each octet can range from 0 to 255. Now, the International Standards Organization, ICANN, which we've mentioned in a previous module, is in control of how these IP addresses are leased and distributed out to individuals and companies around the world. Now, because of the limited amount of IP addresses, the default IPv4 addressing scheme is designed and outlined with what are called classes. And there are 5 of them that we need to know. Now, these classes are identified as A, B, C, D, and E. And each class is designed to facilitate in the distribution of IP addresses for certain types of purposes. Now, the first class, a class A, allows you to have, is designed for really large networks, meaning that it does not have a lot of networks because we only have a few of them, and that is because a class A range goes from 1 to 127 in the first octet, meaning that the remaining octets are reserved for nodes. And so we see that we don't have a lot of networks. We only have 126 networks, 1 to 127. But we do have up to 16.7 or 0.8 around about million nodes that can be on this network. And so we have so many nodes for so few networks. And so this is really for very large networks. And there are some specifically reserved addresses in this as well, and we'll talk about those in just a minute. Now with Class B, here we have 128 to 191. And these are called Class B. They allow for a lot more networks and fewer nodes, which makes sense. Now, the default subnet mask for a Class A, which might make this a little clearer, 255.0.0.0, whereas for a Class B, it's 255.255.0.0. Now, as you can tell, the class is actually determined by the very first octet, the number in the first octet. And it's important to then, therefore, memorize these numbers because you'll see on your exam, they'll ask you which class is this IP address a part of. If it's between 1 and 127, you know it's a Class A. If it's between 128 and 191, you know it's a Class B. If we get to a Class C, now we have a lot of networks and not a lot of nodes. And you can see that these are 192 to 223 in the first octet. And the default subnet mask for this is going to be 255.255.255.0. And if you remember, that gives us only this octet for nodes and all of these octets for networks. This is usually one of the most recognizable for home networks because we have the 192.168.0.1, for instance, that is going to obviously fall into this Class C. Now, there are two other classes. They're not very common, but they're important to be able to recognize. There are Class D IP addresses, which are only used for what we call multicast transmissions. And these are for special routers that are able to support the use of IP addresses within this range. You don't really need to worry about this for much application unless you're dealing with a lot more advanced stuff. And these deal with 224 to 239. Finally, we have Class E, which is from 240 to 255. And these are really for experimental reasons. So we're really not going to see these in much play. The ones you really want to be familiar with are these first three classes, A, B, and C. Remember, 1 to 127 is a Class A, 128 to 191 is a Class B, 192 to 223 is a Class C. If you can remember those ranges, I would commit them to memory. You'll be good to go for the exam. Now, within each of these classes, there are a number of addresses that are not allowed to be assigned or leased for specific reasons. These are what we call reserved and restricted IP addresses. Now, we've mentioned the 127.0.0.1 or the local loopback or the local host IP address before, which can't be assigned because it's reserved for me, for myself, for I. This means that this address is used when I want to address myself. So if I wanted to, for instance, assign myself my own name via DNS, and my name was me would link up to the IP address 127.0.0.1. And that way it's going back to myself. Now we're really going to use this for mostly diagnostic purposes if I want to double check to make sure, for instance, that TCP IP is running correctly. And it's also going to be used for programmers and such like that. Now the address 10.0.0.0 is also restricted, and it's not available to use because, again, this a host address can never have all zeros. Conversely, the addresses that have all ones, for instance, 255.255.255.255, cannot be used for addresses. Obviously, this one can't because it would sort of ruin the use of a subnet mask. But even if I had something like 192.168.0.255, I can't use that because that's what's called a broadcast address. And so it's just simply reserved for that. This means that if a message is transmitted to a network address with all ones in the host portion, or 255, that message is going to be transmitted to every single device on the subnet. It's called a broadcast, and we talked about broadcast before. Finally, the address 1.1.1.1 cannot be used because this is what's called the all hosts or the whois address. So these basically, whereas 127 is for me, 1.1.1.1 is for everyone. So these we can never use. The important one I really want you to remember here is this one, and you're going to want to remember that, for instance, 255 in the host portion can never be used. Again, not only because that's going to ruin a subnet, as we've talked about, but also this is reserved for what's called a broadcast address. Now, there are portions of each class that are allocated either for public or private use. Private IP addresses are not routable. This means that they are assigned for use on internal networks, such as your home network or your office network. When these addresses transmit data and it reaches a router, the router is not going to route it outside of the network. So these addresses can be used without needing to purchase or leasing an IP address from your ISP or internet service provider or governing entity. So this is how I could create an internal network in my home, and I don't need to go register it, and I might not be able to access the internet, but I don't need to register it. If I want to go out to the internet, then I can share using devices and resources we've talked about previously and we'll talk about later, a public IP address with all of the internal devices that are configured using private IP addresses. Now, since these are not able to be used externally to our network, these IP addresses can be used by as many devices as necessary, as long as we never double over one IP address per device. So the Class A private IP address range Remember we talked about 10.0.0.0 because we cannot have zeros, right? Remember 10.0.0 and 255 we actually cannot assign, but any address in between that, so 10.1.126.5 would fall into what's called a private address range. And you might see this in your home router as well. So this makes it easily discernible from other addresses in its class. Anything that has the 10 to begin with cannot be used on a Class A network or any network except privately. We also have a Class B private exchange, which is 172.16.0.0 through 172.31.255.255, and Class C, which is 192.168.0.0 through the 255 to 255. This one you might have seen the most. This one I'm guessing you've seen the least. This one's probably the second most common, the 10 dot. So if you have an internal network at your home, you might have your address on your computer right now, for instance, if it's not connected directly to the network, if it's connected to a router, might be something like this, or like this, or even like this, all right? That's because these are each private addresses. It's important that you commit these to memory as well, because these will appear on the exam. And remember, the important thing with a private IP address, as I mentioned right here, is they're not routable, and I don't need a lease to use them. So when tasked with subnetting a network, you need to understand how to calculate how many hosts and how many networks are available. If we want to determine the number of hosts that are available, we apply this formula, 2 to the x minus 2. And this is where x equals the number of node bits. And that's after we break it down from decimal to binary. Now, the reason for the minus 2 here is because, again, we cannot use a .0.0.0 address or a .255.255.255 address, which would mean all zeros or all ones in the subnet. And so we need to make sure, rather in the bit, right, when it's broken down. And so we need to make sure that this is the case. We also need to know the number of networks, and to do that, we're going to do 2 to the y minus 2, where y equals the number of network bits. So let's take a look at this. If we have the IP address 162.85.120.27, and we have a subnet mask of 255.255.255.0, by the way, we can look at this and we automatically know that 162.85.120.27, this looks like a Class B IP address. And the 255.255.255 is actually our default Class C subnet. So this is not the default that we're working with here. So we need to figure out some information here. So let's break it down into bits, and I'm going to do that here. And if you wanted to check my math, you could. Now the number of network bits is right here, the y, and the number of node bits is right here, the x. So if we pop this into our equation, the number of possible hosts we have is 254, and the number of possible networks is over 16 million. If we go back to that table we saw a few slides ago, we'd see then that that's why we have a default for Class B and a Class C networks, is we can see how many networks are possible and how many hosts are possible. Now, why would I want to know this? Well, let's say that I have to divide up my network, and I want to have a certain number of networks and a certain number of hosts. Well, if I only need 5 networks, but I need 30,000 hosts, I'm going to be in major trouble here, because now I have to divide this up so much, I'm wasting a lot of networks, and I don't have enough hosts. So we want to determine how we can do this to reduce the amount of waste. And we're going to talk about that in just a bit. Going back to something called a default gateway for a second. For any device that wants to connect to the internet has to go through what's called a default gateway. This is not a physical device. This is set by our IP address settings. It is basically the IP address of the device, which is usually the router or the border router that's connected directly to the internet. If, for instance, we had other routers in here, this is going to be the gateway. And so 3 things need to be configured on any device that wants to connect to the internet. We've talked about it. We need to have an IP address, a subnet mask, and this is the new one, a default gateway. So this is the device that's used when I want to communicate with the internet. And it's not used when communicating with devices on the same subnet. This is why it's called a gateway. Think about it as your gateway out to the network. Most often, and more often than not, as I mentioned, this is going to be the router. So if you have at home, for instance, a router that's 192.168.0.1, that is also your default gateway. And if you went in and did an ipconfig all, something we'll take a look at later, in command prompt, you'd be able to see then your default gateway is this address. Basically, it means, hey, I don't know, I want to get up to the internet. I don't know how to get to Google. I'm going to ask my default gateway. The default gateway then takes care of everything else, and then the information comes back, and it sends it out to you again. Now, there are a couple different ways of implementing custom IP addresses. We previously described how we could use custom subnets, and with that method, a custom subnet mask and an IP address is what we call ANDed, if you recall. And together they allow the node to see the local network as part of its larger network. Now, each customized subnet is configured with its own default gateway, allowing the subnets to be able to communicate with each other. Now, another method of doing this is called VLSM, or Variable Length Subnet Mask. And by using this, we're going to assign each subnet its own separate customized subnet mask that varies. Now, the VLSM method allows for a more efficient allocation of IP addresses with minimal address waste, which I was just talking about. So, for example, let's take a situation in which a network administrator wants to have 3 networks, and I have a class C space. Now, just so you know, some of this is very outdated, and we're not going to see it used a lot of the time. That being said, Network Plus really wants you to know about it, so we're going to cover it. So, I know I need to have 3 different networks or subnetworks. And I know on the first network, I want to have 4 hosts. On the second network, I want to have 11 hosts. And on the third network, I want to have 27 hosts. Now, in order to accomplish this, I could use the subnet mask 255.255.255.20.224. And for each of these subnets, if I was to add this out, right, 1, 2, 3, 4, 5, 6, 7, 8, that's 255, 1, 2, 3, 4, 5, 6, 7, 8. That's 255, 1, 2, 3, 4, 5, 6, 7, 8. That's 255. Let's write 224 in bits. All right, let's go through our calculation again here. I'm just going to do this because it never hurts to do this a couple times. So let's write all of these out. Great. All right, we have 1, 2, 4, 8, 16, 32, 64, 128. Now we remember that subnet masks have to have continuous ones. So that's 128. 128 plus 64 is 192. Plus 32 is 224. So then if we broke this down into bits, this is what it's going to look like. Okay? So let's write that out here. And if we do our calculation, we know we need to have how many hosts? Well, we need 4. So let's do our calculation. 2 to the 1, 2, 3, 4, 5 power. Right? We're going to figure out how many hosts. That equals, we already know, is 32 minus 2 means that we can have up to 30 hosts on this subnet. So I'm wasting, in effect, 26 addresses on this subnet, 19 on this one, and 3 on this one. I'm not really doing a good job because I've had to apply the same subnet mask to every single IP address. And in doing so, I'm wasting a lot of my possible addresses. Now, if I used VLSM instead, I'm just going to erase all this. I could do 255.255.248.240 and .224. Now, remember, 248, if we wrote that out, I'm just going to really quickly All right, and you can double check my math here. If we do 248, that is going to be 1, 1, 1, 1, 1, 0, 0, 0. All right, and then if we do our calculation, 2 to the 3, because we have 3 host bits, what does that equal? 8 minus 2. Well, now we have a possibility of 6 hosts. So what is our waste? 2, because 6 minus 4 equals 2. A lot better, right? If we do the same thing with the next one, and you were to do the same thing I just did, that would look 1, 1, 1, 1, 0, 0, 0, 0. We did the calculation. Again, 2 to the 4, because now we have 4 bits, minus 2, which equals 16 minus 2, which equals 14. So now I'm only wasting 3 bits, because 14 minus 11 equals 3. And finally, 224 is the same. Remember, that was 30 bits, or 30 hosts rather. 30 minus 27 is 3. So doing this variable, we are a variable subnet mask, we're no longer wasting as many host addresses. So by utilizing this, we're going to appropriately plan and implement a scheme, and it allows us to use our space much more effectively. Of course, the negative aspect of this is it's a lot more harder to scale. And if I want to add nodes to these customized networks, I might have to go around and change all of the subnet masks as well. Now, CIDR, which is CIDR, which stands for classless inter-domain routing, is also commonly called supernetting, or classless routing. It's another method of addressing that uses the VLSM, but in a different way as at the 32-bit word. So the notation is much easier to read because it combines the IP address with this dash after it. For instance, the number is what denotes the amount of ones in the subnet mask from left to right. So if we look at this notation right here, we have 192.168.13.0/23. Well, the 23 means there are 23 ones from left to right in the subnet mask. Okay, and now if we were to convert that, this allows for a possible amount of host addresses, 2 to the 9th minus 2, which equals 510 addresses. So this allows for more than one class-full network to be represented by a single set. Basically, we can now break it up further into smaller subnetworks. If we look at 3 of the most easily recognizable ones, I'm just going to erase this so we can get a better look here. The /8, the /16, and the /24. We can see that these translate basically over to the basic Class A, Class B, and Class C networks, right? Because /8, Class A, that means it's 1, 1, or 1, 2, 3, 4, 5, 6, 7, 8, dot 0, dot 0, dot 0, which would mean 255, dot 0, dot 0, dot 0, which is our default subnet mask for Class A. Because, again, this is my network ID is the first octet, and the node ID are the last ones. And you can see that that would fall out for the next ones as well. So because of the ease by which it is, we can subnet networks this way, because of readability and efficiency, CIDR notation has become extremely popular and widely adopted. Most of the internet, in fact, has become classless address space because of this, meaning that we don't really use classes, and when we get to IPv6, we're not going to see it at all. Now, again, this is very complex. The important thing I just want you to remember on this whole thing is that if you see this dash after an address here, you know exactly what the subnet mask is, and then you can backwards engineer or forward engineer the IP address or the network ID or node ID. So just to review some of the points that we covered here, we started by outlining the IPv4 addressing scheme. We looked at the 5 classes. The 3 I really want you to be aware of are A, B, and C, Remember, A is anything in the first octet that's 1 through 127. With class B, we're looking at anything from 128 to 191. And with class C, we're looking at anything from 192 to 223. Anything else here, we're really looking at experimental and stuff that we don't really need. Remember these ranges for that first octet. It's easy then to determine what class we're looking at. Okay, so we also described the reserved or restricted IP addresses. For instance, we can't have anything with a .0.0.0 or with a 255.255.255 because these are our multicast addresses. And we also can't have anything with 127.0.0.1 ever or 1.1.1.1 because these are both, one's the local host, one is the whois address. We then looked at private IP addresses. Remember, we had 3 different ones each for each class. For class A, it was anything 10.x.x.x. With class B, it was 172.16.x.x through 172.31.x.x. And the one you're probably most familiar with is the class C, which is 192.168.x.x. Remember that you can see what class they're in by looking at this. And most importantly, class A private IP address can allow for the most networks, the most nodes, the fewest networks. Class C is going to be the complete opposite. I'm going to allow for the most nodes, the most networks rather, but the fewest nodes, okay? And again, remember these ranges because they will come up. What does make a private IP address? It is not routed past a router onto the public network, okay? We also talked about the IPv4 formulas, which allow us to determine how many hosts or how many networks are allowed on a network. And that is where the X or the Y equals the number of host or network bits. We defined the default gateway, which is what I need to get out to the WAN. It's what a local device, a node on the local area network, needs to go to this default gateway. And finally, we defined the 2 custom IP address schemes, the one which allows me for variable subnetting, and the other, CIDR, which allows me to use a slash and then put a number, that number representing the number of network bits in the subnet mask. Right? So the most popular, of course, 24 would be for a class C, 16 would be for a class B, and 8 would be for a class A, because if we had a /8, that would mean the subnet mask is 255.0.0.0. Data delivery techniques and IPv6. Now, we've talked a lot about IP addressing when it comes to IPv4, or the Internet Protocol version 4. But fairly recently, IPv6, or IP or Internet Protocol version 6, was released and has now begun to be implemented across the world in every network situation. So in this module, we're going to discuss the core concepts that are involved with IPv6 addressing and some of the data delivery techniques as well. So at the completion of this module, we're going to have a complete understanding of the properties of IP version 6 or IPv6. And we're going to be able to differentiate between IPv6 and IPv4, which is the one we've been talking about up until this point. As a reminder, IPv4 is that IP address that is 32 bits and divided into 4 octets. And we're also going to outline some of the improvements in the mechanisms of IP version 6 and why we needed to have another version of IP addressing. We're also going to cover the different data delivery techniques, as well as what a connection is, different connection modes, and we touched on these briefly, such as connection-oriented and connection-less, and their transmit types. Finally, we're going to go further into data flow, or flow control, which we've talked about a bit, and we've mentioned a bit. buffering, and data windows. These are all techniques that allow data to be sent over a network in varying ways. And finally, also, we're going to talk about error detection methods. That way we know when data arrives on the other end, we can double check it to make sure it is the data that was in fact sent. So in the last module, we learned about the IPv4 addressing scheme, and we talked about some aspects of how it's implemented. Now, IPv6 is the successor to IPv4, and it offers a lot of benefits over its predecessor. The first major improvement that came with this new version is that there's been an exponential increase in the number of possible addresses that are available. Several other features were added to this addressing scheme as well, such as security, improved composition for what are called unicast addresses, header simplification and how they're sent, and hierarchical addressing for what some would suggest is easier routing. And there's also support for what we call time-sensitive traffic, or traffic that needs to be received in a certain amount of time, such as voice over IP in gaming. And we're going to look at all of this shortly. So the IPv6 addressing scheme uses a 128-bit binary address. This is different, of course, from IP version 4, which again uses a 32-bit address. So this means, therefore, that there are 2 to 128 power possible addresses, as opposed to 2 to the 32 power with IP address 4. And this means, therefore, that there are around 340 undecillion, I'm going to write that out, so that's a word that you probably haven't seen a lot, undecillion addresses. And to put that another way, it's enough for 1 trillion people to each have 1 trillion addresses, or for an IP address for every single grain of sand on the earth times 1 trillion Earths, give or take a bit. So if the 128-bit address were written out in binary, it would be 128 ones and zeros, because that is binary. And even in decimal form, that's pretty hard to read and keep track of. So because of this, we use what's called hexadecimal as the format in which IPv6 is written. And if you imagine from the name, hex, binary is a base 2 system, meaning that we take everything to the power of 2. So we have the ones place, and then we have the 2 place, and then we have the 4 place, and so on and so forth. With decimal, which is a base 10 system, we have the ones place, the tens place, the hundreds place, which is 10 times 10, the thousands place, and so on. With hexadecimal, though, we're looking at a base 16. So every single digit has a possible 16 different options. So we'd have a ones place, which we always start with a ones place, and then a 16s place, and then so on and so forth. Now, the way we do this is that every digit, as opposed to decimal, where we have 0 to 9 options for every digit, and binary, where you have either 0 or 1, with hexadecimal, we can either have 0 to 9 or A through F. If we add this up, we have 10 options here, 0 through 9, and then A through F, we have 6. So a hexadecimal number is going to be a combination of anywhere from 0 to F. A would be 10, B would be 11, C would be 12, and so on and so forth. So when you see this written out, that's what that means, okay? Now, the address is broken up into 8 groups of 4 hexadecimal digits. And these are separated by colons. Now, I'm going to show you this in just a second, but there are also a couple of rules when it applies to when we come to readability. So the first rule is that, let's say this is our hexadecimal IPv6 address. You notice, first of all, 1, 2, 3, 4, 5, 6, 7, 8, right? There are 8 groups of 4 hexadecimal digits each. And of course, each one of these digits has 16 possible values. Okay, so let's look at 2 rules. And these are also not only readability rules, but what we call truncation rules, meaning this is how we can shorten an IPv6 address since they can get quite long. The first rule is that any leading zeros can be removed. So if we imagine any leading zeros, I'm going to circle them right there, right here, right here, and if we wanted, we could even consider these leading zeros. And therefore, if we rewrite this out below, you'll see we're going to remove all the leading zeros. And that allows us to shorten our address. Now, we could also, if I was just going to take this one step further, I could also shorten these zeros if I so wished, and just leave 1 0 there. Now, no matter how you write out the address, the rules are put in place in a way that you can always go back to the main address. And so you don't have to worry about, you can sort of pick and choose. There are best practices, but the computer's always going to be able to figure it out, okay? Now, the second rule is that successive zeros or successive sets of zeros can be removed, but they can only be removed once. So, any sets of successive zeros, and here we see one set, or 2 sets rather, of successive zeros, can be removed and replaced with a double colon. Now, the reason we can only apply that once is, let's say these zeros we had another set of zeros over here, and we truncated those. We can add up, right? We know there's 1, 2, 3, 4, 5, 6 sets here. So we know that this represents 2 sets of missing zeros. But for instance, if we had, 2 other sets here and we removed those, we might not know whether it's supposed to be 1 set and 3 sets, or 2 sets and 2 sets, and so on and so forth. So we can only do this once, because when we add them back, there's no way to know, where that would sort of lie. Now, I'm just going to erase this for a second, because we can even truncate this more. We've applied this rule, so this applies this rule, this one has applied this rule, but we can apply both rules, right? So we can remove these leading zeros here and actually write this out as 2001 D8 88 A3 double colon, which means that those are successive zeros, 3E 70 7334. Now, I just want to sort of follow up and explain, write out what I was just talking about with why we can't have more than 2 sets of successive zeros, okay? Let's say that we have zeros here as well, okay? So I'm going to rewrite this out. We have 0, 0, 0, 0, colon, 0, 0, 0, 0, colon, 0, 8, A3, colon, 0, 0, 0, 0, 0, 0, 0, 0, 8C, 3E, 0070 7334. Okay, let's first apply our first rule, which is that leading zeros can be removed. So we rewrite this, and we're going to get this. Okay, now we're allowed to remove 1 set of successive zeros only, which is the second rule, okay? But let's do it twice and just see what happens. So let's say we have a double colon here, 8A3, and then we have another double colon, 8C3E, 707334. Now, let's say we want to expand this back out to its full version. Well, if we have these successive zeros here, we don't know if this would be written out 0000.8A3 because from what we're seeing here, theoretically, we could put 3 zeros here and 1 0 here, right? Or we could do it the other way around. So the reason we can only do it once is because then mathematically we know exactly how many belong when we do that, all right? So hopefully that helps clarify the reason behind the successive zeros being removed. All right, now what this also means is that if you remember a loopback address, an IPv4, the loopback was 127.0.0.1. Well, we also have a loopback when it comes to IPv6. That's all these zeros to 1. But because we can apply all of these rules, we can truncate this to simply this. All right? So this is important to remember. These rules are important to remember. The other thing I want you to remember is that hexadecimal is 0 to 9, A to F. So they might show you something and say which of these is not a valid IP. If it has a letter, say a G or an H, then you know it's not going to be valid. And here we can check. Here's a D. That's good. Here's an A. That's good. C, good. E, good. So this is good to go, right? If we had an H or a G or an X, for instance, then we would know that the IPv6 was incorrect because there's no hexadecimal symbol X. So the IPv4 addressing method is really different from IPv6 addressing, and it's comparatively it's lacking in many areas. First, as we've talked about, we're using a 32-bit binary address in IPv4 versus a 128-bit binary address in IPv6. And of course, this greatly increases the number of possible IP addresses. I think around February of 2011, all of these IP addresses had been leased, and so there weren't any addresses left. I think we had something where at like 4.8, 4.7 billion, right? And all those were gone. And so we were depleted of all of our IP addresses. So this is why we had to transition to IPv6, because now we have that undecillion address, which again is if there were a trillion people, they could each have a trillion addresses. Now, another major difference between these two is that IPv4 utilized the classless interdomain routing notation, if you remember, which had that slash and then a number of bits. Well, in IPv6, this isn't necessary, and IPv6 actually has a subnet size of 2 to the 64th power. Now, if you remember that the total IPv6 is 2 to the 128, then what you realize is that the first half of the IPv6 address, so if we were to write one out again, let's say 208A, A364, 92BF, 1000, right? Okay, so then we're going to have 4 more on this side. The first 4, which again is the first 64 bits, that's the subnet. So now we've integrated the subnet into the IPv6 address, which is the benefit. Now we don't have to sort of have this extra written out CIDR thing. So it's been standardized. It's always 2 to the 64. We always know the subnet or the network node is on the first section, and the node ID is on the second section, the other 2 to the 64. So this really helps simplify things to a great extent. Now, obviously, one of the issues is we're going to underuse a lot of the addresses. We're going to underuse many of our addresses because we're never going to have to really use this many subnets, or perhaps not even that many networks, right? But there are so many other benefits that it has with routing and efficiency and simplified management that it sort of makes up for it. And so that's why we're going to make that sacrifice. Now, in terms of domain name systems, with DNS, when we talked about, for instance, a google.com going over to, say, whatever that IP address is, I'm making this one up, obviously. It's not a real one because we're in a private IP. But this was called an A record, right? So a server would have something, or a DNS server would have something called an A record, and that A record had this information in it. All right. Now, when we're dealing with IPv6, we're utilizing a quad A record for this mapping. Now, it can also use the same A record, but this quad A record can be used as well. So if you see 4 A's, what we call a 4A record or a quad A record, then you know we're using IPv6. It's one of the differences. And again, these are the records that are used to map IP addresses to what are called fully qualified domain names. Now, while comparing these two schemes also, IPSec, which stands for IP security, is another aspect that we need to consider. In IPv4, IPSec is optional. It's widely used for secure traffic over IPv4 communications. But when we dealt with IPv6, IPSec was designed for it. And so it's required from the original specification, and therefore all communications that are working over IPv6 are automatically falling under IPSec. So it can be considered in some ways optional, I guess, but it is required use from the get-go because it was built into IPv6. Now, the IPv6 scheme can also handle a much larger packet size. The packet size for IPv4 is 65,535 octets payload. When we get to IPv6, we're dealing with a 4.295 billion octets of payload. So obviously, these are a lot bigger. These are what we call jumbograms. As a result, you can imagine that if we want to deal with IPv4 and we're on an IPv6 network, we're going to have to make up for this. Now, if you recall, when we were talking about Ethernet, we also were talking about the header sizes and all the information that was contained in there. Well, the header size for IPv4 and IPv6 is also very different, which actually makes these two protocols not compatible with each other. So IPv6 is not compatible with IPv4. And so the way we're going to communicate with an IPv6 over an IPv4 network, if we need to, is by tunneling the packets. In other words, we take an IPv6 packet, and we literally wrap it around, or we wrap around it an IPv4 packet. And so we tunnel the IPv6 packet inside of the IPv4. Now, this allows it to communicate, but this is also what we call a dual stack. In some cases, we can have what's called a dual stack, where we have an IPv4 and an IPv6, and so we can choose which one to go over, and then this tunneling is not going to be necessary. Now, we don't really want to tunnel because obviously the payloads are so much different in size that it's going to cause all sorts of trouble. So what we'll try to do is create this dual stack in which we have one network and the other, and they're both operating sort of side by side. If we can't do that, then we have to use tunneling in order to move the IPv6 data over an IPv4 network, which might be necessary even if the IPv6 data is traveling through an IPv4 network. All right, so we've compared these. Let's talk about some of the improvements that IPv4 did not have that IPv6 does. Starting with some security and privacy measures. If privacy extensions are enabled with IPv6, then we have something called an ephemeral address, which is created. And this is used as a temporary and random address that's used to communicate with external devices, but the external device doesn't know the true address of the internal device. And so this improves the privacy and security for the user. And this is what we call a privacy extension. And it does have to be enabled from sort of a router point of view. Now, another improvement is a better composition of what we call the unicast address. What this means is that IPv6 uses a unicast addressing structure to replace the classful addresses of IPv4. This offers a lot more flexibility and efficiency with addressing, and depending on the category of the unicast address used, there are different functions for each, meaning that there are different types of addresses that are used, and that way the computer automatically knows what the function is. The first is called a global address, which is sort of like the public or routable addresses in IPv4. If you recall, most addresses could be routed. Those are what we call global addresses. We also have site local addresses, which are essentially like the private addresses or non-routable addresses that are not routable to external networks. If you recall, these were, for instance, the 10.0.0.0 through 10.255.255.255, and then the 172.16 through 32, and then the 192.168. Those are the private addresses. Well, in IPv6, we call them site local addresses. We also have something called link local addresses, which are basically comparable to PIPA addresses in IPv4, and we're going to talk more about what those mean in just a little bit later. But just to give you a little heads up, and we have talked about it with A+, if you were around for that, this is automatic private IP addressing. And we need, because every device needs an automatic IP address, if it's not given one by a server, then it's going to give itself one, what we call a PIPA address. And so in IPv6, these are called link local addresses. And finally, there are IPv6 transitional addresses, which are basically going to be used in the time being until we phase out of IPv4. These are used to route IPv6 traffic across IPv4 networks through tunneling, much like I've just described in the previous section. Now, a mechanism built into IPv6 addresses is a field located in the IP header that's designed to guarantee network resources be allocated to services that need time-sensitive data, such as voice over IP. Right? We need that is time-sensitive because I'm talking and I want the person to hear almost as soon as I talk. And so this time-sensitive stuff is built into IPv6, one of the reasons that we use it. Now, another improvement with this scheme, IPv6, is called hierarchical addressing. This eliminates the random allocation of addresses. So connectivity devices, such as top-level routers, are assigned a top-level block of IPv6 addresses. And then segments are added to those with blocks of addresses that are assigned at that level. So basically, it looks like a hierarchy from an IPv6 standpoint. You remember we looked at this sort of topology earlier. Now, IPv6 scheme also has a much simplified header, and it's going to make addressing a lot easier to read. This improves the speed packet routing on an individual packet basis. So obviously, if we're going to simplify how information can get read, it's going to simplify how routing can occur. Now, data in transit is susceptible to a variety of things that could cause it to be delayed, lost, or damaged. And these things can occur on the transmit side and quite commonly on the receiving side as well. So the method the data is delivered makes a huge difference in whether the data is going to arrive at the destination correctly and efficiently. So depending on the method of delivery, there can be error detection, which would mean we detect that there are errors, and error correction, which means we not only detect, but we fix the errors when these recovery mechanisms are used. Now, an important aspect of the data delivery begins with the actual connection itself. So depending on the type of connection service used is going to give us an idea of what sort of delivery options are available. So, a connection in terms of networks is the logical joining of two network devices through a specified medium that is established and maintained for a period of time during which the session exists. In other words, the connection is what allows data to be transferred between, say, my computer and a server computer. Now, in networking, and specifically in IP networks, there will be connection services that attempt to provide data integrity and reliability. Now, there are generally three types of connection services that we see when we discuss certain protocols. And we've talked about these in some way, shape, or form, but it doesn't hurt to sort of go over them in a little more specific detail. The first is an acknowledged connectionless service. In these, the connection isn't created. However, when data is received by the destination, there is an acknowledgement of receipt. So website communications use this type of service. A great metaphor to think about this would be, for instance, a delivery receipt with regular mail. So it's not certified. We're not going to get a signature, but what we do is we get a receipt that it has been delivered. Now, with unacknowledged connectionless services, there's no acknowledgement sent unless the application itself does this. This could also be considered simplex communications, which we'll talk about in just a second. So this is just like regular mail. We send it, we drop in the mail, there is no acknowledgement, okay? Acknowledged at least has an acknowledged that data has been sent, but there is no connection made, right? There is no established session made between the receiver and the sender. Finally, we have connection-oriented services. And by the way, when we talked about these connectionlesses, you recall this is like UDP, which is connectionless, and IP. Here, connection-oriented, we're looking at TCP. Now, these are where error detection and correction are available, as well as some flow controller packet sequencing. In other words, this would be like certified mail. Now, there are also three types of connection modes that we're typically going to use. There's simplex, half duplex, and full duplex. With simplex, this is one-way communication only. This is sort of similar to FM radio broadcast, right? You turn on your radio, you tune in, and you can receive, but you cannot send data. Now, we also have half duplex. This is two-way communication, but only one at a time. This is like a pair of regular walkie-talkies. Only one device can transmit at any one time, which is why we have to use those code words, right? Over, and out. So this is like a walkie-talkie. Finally, we have full duplex, which is two-way and both ways simultaneously. This is similar to the telephone, in which we can talk and listen at the same time. In some ways, we have trouble understanding each other as a result of it. Now, in networking, devices are designed to receive and transmit data at different speeds, and with different sizes of packets as well. So certain devices are not going to be able to handle as much data as others at one point or another. We talked about this briefly with MTUs and MTU black holes. So flow control is the managing of amounts of data and the rate at which the data is being transmitted over a network connection. Flow control is necessary to help prevent devices from being overflowed with data. Now, some devices, when there's too much data is received, are going to potentially shut down to prevent certain attacks, or simply are going to drop packets that are too large because they're going to cause delays. On the other side of the scale, if too little data is being received by the device, it may just be sitting idly by waiting for the remaining packets. In this case, it's simply a matter of efficiency. So there are two main types of flow control that are covered on the exam: buffering and data windows. Buffering is a flow control technique where a portion of the memory, either physical or logical via software, is used to temporarily store data as it's being received in order to regulate the amount of data that's being processed. Buffering may be used to maintain data consistency as well as minimize overloading. Now, RAM uses a type of buffer when data is being read from its cache, right? So remember we talked about RAM, and that was what we called cache. Now, with buffering, there is a potential concern because what if the buffer becomes full? Well, when receiving node's buffer reaches a certain capacity, it actually transmits a squelch signal. I'm going to write that out just not only because it's a great word. that says stop transmission or slow down your transmission so I can catch up. Now, a common place we're going to see this type of flow control is when we're streaming movies. You might have seen buffering when you're using movies, for instance, on YouTube or on Netflix or any of these sites. The idea is, if there's a problem with our communication, we have a little buffer of data, so that way we're not going to see a dip in quality of the film. Now, another type of flow control is called data windows. The data window refers to the amount of data being sent, and it can either be a fixed amount or it can vary. And these are fixed length windows or sliding windows rather. If you think about the window, and I put the data inside of it, we can either have a window that is a specific length, like this, or a window that can possibly get smaller based on the data. And that's what fixed length and sliding windows are. So to go a little more in depth into these, with fixed length windows, the size of the packet of the data being sent is determined by the sender. And the rate of transmission is determined by the receiver. So the size is typically going to be pretty small, and overall this is going to be fairly efficient. The other thing to remember is that the packet size is always going to remain the same. It's never going to change. So if I need to send 10 packets, they're all going to be exactly the same size, or as much as I can draw them as such, and so on and so forth. Now with a sliding window method, it's a bit different. The sender begins to transmit data typically with a small number of packets, and with each transmission, it waits for an acknowledgement or ACK packet receipt. Now, with each receipt, this contains the current maximum threshold that can be reached, and then the transmitter is going to begin increasing the number of packets by a specified amount. In other words, it's going to start sliding that window from here over. Now, it's going to continue to increase this over and over and over until we reach a maximum potential. At this point, we're going to start getting some congestion, and so the receiver is going to send another ACK saying, listen, you need to slow down now, and this is a good rate. This method is really going to allow for minimal data traffic congestion and a lot of throughput. And depending on the amount of traffic, the size of the window can really vary dramatically, and so this really gives us a lot more flexibility. If you imagine if I have a home that has a whole bunch of regular windows, I'm going to want sliding windows. Now, if I have a home with all these similar windows, everything built the same, then I can use a fixed length window. But this one's going to give me a lot more flexibility. Now, error detection and correction is an important aspect of how we know our information arrived at the destination unhindered and unaltered. One method achieves this by attaching supplemental information at the end of the footer that pertains to its contents, and the receiving station is going to look at that data and compare it to the data it received. If the data matches, it's going to consider it error-free. If not, the data is going to be requested to be retransmitted. Now, when an additional correctional component is added that allows the data to be rebuilt in the event of an error, this is going to become an EDAC, or error detection and correction. Now, parity check is a process where an extra bit is added to every word of data. And the receiving station can look for the bit on this word-by-word basis. Remember, we're talking about words. We're not talking about language. We're talking about words as far as data goes. And so it can look at these, and therefore it can determine any errors that are built in. Because parity adds this extra bit to every word, this method takes a little bit of overhead. So it does add not only extra resources, but some more data in there. Now, with something called CRC, or cyclic redundancy check, a code is added to every block of data through a mathematical operation, which is also referred to as hashing. Now, this code is added to the end of the block, and then it's transmitted. When the receiving station applies this hashing method, this mathematical operation, to the code, then it should get the same data. And if it doesn't, then it knows there's a problem, and it can request it to be resent. Like parity, CRC is also going to add a certain amount of overhead because it takes data and calculation time. All right, so now just to review some of the topics we talked about. We talked about the IPv6 addressing scheme. Specifically, we talked about it's a hexadecimal, 128 bits, divided into 8 sections. We also compared and contrasted IP version 6 with IPv4. We saw that IPv6, for instance, has IPSec built in and has a whole bunch of other improvements and mechanisms, such as data delivery, time sensitive, and so on and so forth. The important thing I really want you to know about IPv6 is that it does not require a subnet, and we need to recall all of the truncation or readability rules, which include removing leading zeros and combining successive sets of zeros, but only once. We also explained the different data delivery techniques, and we defined a connection, the different connection modes, whether they're acknowledged connectionless, simply unacknowledged connectionless, or connection-oriented. We also looked at the different transmit types, including simplex, which is one-way, half duplex, which is like our walkie-talkie, and full duplex, which in effect doubles our bandwidth. We also explained flow control, buffering, and data windows. We use buffering a lot when we're talking about videos. In data windows, remember we talked about the fixed and sliding windows. Finally, we outlined error detection methods, including parity, which adds an extra bit to every word, and CRC, or cyclical redundancy check, which uses hashing, a mathematical operation, so that we can ensure the data that was received was also the data that was sent.
Now, we actually covered IPv6 earlier, however, as per usual, some new ideas have been added to the syllabus. So what I'll do here is I'll review some areas that you've already covered with Josh, just with my own take, and then we'll go into the new stuff. So IPv6 addressing, address types. New is a neighbor discovery protocol, which is part of IPv6 built in. The EUI64 addressing is new. Tunneling types is new. So IPv4, which is obviously the precursor to IPv6, created a long time before we had home computers. The computers were pretty expensive and big, probably the size of any room in your house. So nobody foresaw that people would be using home computers, just like when the telephone was created. I think one of the first comments was, why would I need to phone anyone? So there we go. So it was just, the scheme was designed just to cater for commercial enterprises only, so we didn't think we were going to run out. Lack of a simple auto configuration mechanism. So eventually we had DHCP was created, which works well. Obviously it's got some drawbacks. IPv4 has no security built in. Again, nobody realised that there was no such thing as hackers, obviously, when IP was brought out, because it hadn't been invented yet, so nobody thought that we needed to have it built in. IPv4 is hard to use with mobile devices, especially when we're using the cellular networks. IPv4 needs massive routing tables required over the internet. Internet service providers have huge tables for routing all the IP traffic. There's only around 4 million addresses available. We actually ran out of IPv4 addresses some time ago, and around 50% of the traffic going over the internet at the moment is IPv6, which is why we need to know about it. So IPv6, there's that many addresses. I don't even know what the numbering system is called for calling out that many, but for every person alive, there's many millions of available addresses. Now NAT can be used with IPv6, and you'll read some documents about NAT PT. Not really used. There's no need to NAT because there's just no shortage of addresses really. Security is built into one of the fields in the IPv6 packet. We have address auto configuration, which is a major part of IPv6, and it's plug and play as well. So things like when you enable IPv6 on an interface with most devices now, it actually self-configures an IPv6 address. We do not have broadcast on IPv6, we'll come to that later. It's built to work plug and play with mobile devices again, which is handy. So the addresses, there's several RFCs. One of the main ones is 1884 if you want to read it. It's 128 bits. Each of these bits is divided into 8 groups of 16 bits, and then each of those bits is separated by a colon, which is a dot on top of a dot. Hex numbering is used because it's just a lot easier to write out that many bits using hex than it is in binary. It would take forever. The addresses, when you're typing them out on interfaces, is not case sensitive, so you could use caps lock or lowercase and the address will work fine and be accepted. Here is an example of an IPv6, and you can see, if we just come over here, so 8 groups of 16 bits, which we'll go into a minute, divided here by the colon, and another 16 bits, 16, 16, 16, 16, 16, and so on. So if you wrote the address out in binary just for the, I don't know why I should have said D here, sorry, EEDE, but if you change the hexadecimal here, so this is the hex, into the binary value, it's 1 in the, if I go 1, 2, I know you already know how binary works, 4, 8, so 1 in the 8 column, 1 in the 4, 1 in the 2, so 8 plus 4 is 12, 8, 9, 10, 11, 12, 13, 14, so the E is number 14 here, 14 here in hex. Now we've got the D, so we've got 1 plus 4 plus 8, so 8, 9, 10, 11, 12, 13, so D is 13, and then we're back to another 14, 16 bits, 2 bytes in total, so 4 bits, 8, and then another 8, 16 bits, so that's 2 bytes. We can compress the address, so you can remove the leading zeros. Leading zeros are numbers that appear beforehand, so this is a leading zero, This is a trailing 0, so we can't remove these because they've got numbers prior just before. So if we get rid of the leading zeros, for example here, 0, 0, 0, 1 becomes a 1, 0, 7, 8, 9 becomes 7, 8, 9, and this is there to save space and for when we're writing out the addresses. 0 ABC becomes ABC, and you can get rid of the trailing zeros here and just have 1 0. So this address is legal. To write that out, you could possibly have questions in the exam asking you to choose the correct compressed address. You can use a double colon once to represent consecutive zeros. So here we go, we've got all these consecutive zeros here for some reason. Well, we've got rid of them just by having the double colon here, and we've got a double colon here between the 1, 2, 3, 4. So what we've done is just compress all of these zeros, and we've done it again here, and then we could have put it in the second set of zeros, but just to save space we've got rid of all these zeros here. So practice this, work out your own numbers because this is a typical exam type question. Main IPv6 address types: global unicast, unique local, link local, and multicast. You'll note we don't have broadcast. That isn't a legal address. We also have anycast, which I'm not sure if I mentioned here. So the global unicast, this is allocated by the ISP, and then you will get a mask associated, whatever the mask may be. These are routable on the internet, so you can send them out of your company, and they're legal. They're legally recognised. The numbers range from 2000 to 3 FFF in the first 16 bits. Current allocation, there's trillions of these addresses, so the current allocation has come in from 2001. This will last quite some time, obviously. There's a 48-bit provider prefix, and if you check the images of the address packet, you'll see the 48-bit. There's a subnet ID. You can subnet inside the organization if you wish. Subnetting IPv6 is a topic, but it's not in the CompTIA. It is in the Cisco CCNA, and then the rest is the host portion of the address. Now, I'm sure most equipment can actually do this, but Cisco routers can self-generate this part here. So what you would do is, if you configure an interface, you would basically configure whatever the address is, .b, whatever, and then the host portion here, the interface would self-configure. So I've issued, this is on my Windows computer by the looks of it. I've just issued an IP config all /all, and I've seen the IPv6 address that's been allocated here. I think Windows self-allocates these addresses also. Link local address. The prefix for link local addresses are FE80. These are only valid between the link between two IPv6 interfaces. So you've got an internal router, and say for example an Ethernet connection here. Then these addresses will be valid, and these two IPv6 routers can communicate with one another using this link local address. What it can't do is this address in here, it can't be used to reach another device out here. Now if you've got another device, the link local addresses of these two facing interfaces, so for example fast Ethernet here, fast Ethernet here, they will communicate between one another here. Automatically created once IPv6 is enabled. Now these are used for routing protocol communications. IPv6 protocols mentioned in the syllabus, but I don't think, I've left it out for now because looking at all the official guides, there's no questions yet. I will add it later on if that changes though. Traffic isn't forwarded off the local link, certainly not using the link local address. So here's a configuration for a Cisco router. I've enabled IPv6 routing. I've gone to the fast Ethernet interface. All I've done is turned on IPv6 for this interface here, the fast Ethernet 0/0. I've typed end, and then I've said show me this interface. It's down, I haven't connected it to anything, but as we can see, this address, this link local address, has been allocated, self-allocated. This is an important bit here, FFFE, as we'll see in a minute, but basically this is my IPv6 address. I haven't had to write it out manually at all. I've already shown you the Windows one. Unique local, it's an IPv6 version of private IP addresses, so you can use all of these on the inside of your network. You wouldn't be able to route with them onto the internet. Don't think these are used anymore. I think they're actually been depreciated. If you get a question in the exam, here it would be something like this: what prefix is link local addresses taken from? FC00 /7 for your subnet mask. These depreciate site local addresses. So it's site local addresses that have been depreciated. overtaken by linked local, a unique local. So you'd use this on the inside of your network if you want to do any internal routing. What you couldn't do is use it out on the internet though. Multicast addresses are still used very much in IPv6. This is the prefix, so write it down and put it into your study cram notes. And multicast replaces address resolution protocol for IPv6. A use for duplicate address detection. So when you first fire up your interface, I'll talk about neighbor discovery in a moment, but I'll say, just to save space, I'll say this is the address. Obviously it would be the IPv6 address. This interface will advertise out this address to the network, this multicast address, saying I want to use this address X, and if any of these interfaces are using that address, so this is using Y, that's using Z, it will come back and say no, you can't use that address. But in this case, my example here, nobody's using it. All routers must join the all host multicast group of FF02 and then whatever in the middle, 1, so it'll all be zeros and then 1, and the all routers multicast group. This is how neighbor discovery protocol works, so it must be allocated and listening to these two addresses. And if I issue a show IPv6 interface fast Ethernet 0/0, you can see that it's joined these two groups up here, the F2 and the F1. EUI64 addressing is the new part in the syllabus. So I've issued a show IP interface. Sorry, I didn't do IPv6 because I want to see what the MAC address is, because this is how EUI64 obtains the EUI64 address. So this is how, or one of the ways you can self-generate an interface. It uses the MAC address. The 48-bit MAC address, obviously we need 128 bits. 48 bits isn't enough to generate this address. But what it does, it takes the MAC address, it inverts the 7th bit and adds FFFE in the center. So right in the middle of the MAC address, it's going to add FFFE. Make sure you take a note of this for the exam. So we've got 0011. I'll cover why it doesn't say 0011 here. And then here's the AA here. And then you can see the FFFE has appeared here. It's inserted it. And then it carries on with the rest of the MAC address, BBCCDD. So BBCCCD. So this is how it pads out the address. So there's 2 bits, MAC address plus this, but then it does this other bit here, which is inverting the 7th bit. So just to recap what I've already said, we're looking at this part now, 0011. Well, instead of that now we've got 0211. Alright, so going on to the seventh most significant bit. So this is our sample address here. The first 2 nibbles is 1 byte, so this is 0.0. So a nibble, if we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits is 1 byte, which we've covered already. Oops. 1 byte. 1 byte, 8 bits. But what we can do is kind of subdivide it in the middle here. And we can have a nibble here. And a nibble here. Alright, so our first 2 nibbles, 1 byte here, is 0, 0, which would have all the binary bits, basically. Pretty easy to work out. So this here, if you write it out with a nice font is 00000000. So what we need to do is flip the 7th most significant bit. So what we've done is 1, 2, 3, 4, 5, 6, 7, 8. So this is the 7th most significant bit, and what we've done is gone all the way over here to find the 7th bit, and we've flipped it. So whatever it was here in binary, we've flipped it. So 1 flip to 0 flip to be a 1. Now if you wrote that out, this part here, you'd have your 0 would become a 2. That's the 1, 2, 4, 8. 1, 2, 4, 8. Okay, so we've enabled this column here, and our 0 has flipped to a 2. And you can see here 0, 2, 1, 1, and then this is the MAC address. We've got the FFFE in the middle, and then the rest of the MAC address. This is how you work it out. You might get a question on this, so this is why I brought it to your attention, and you just need to practice a few examples. So what would this address be changed to? If you write it down. Alright, so I've just carried it over to the next slide here. So show IPv6 interface, we've got this address here, and we end up with this global unicast address here. And you can see already we've got the FFFE created here. So, and because it might not show you in other vendors, but you can see here there's a clue, it says EUI, so we know your EUI64 is addressing. Well, C2 in decimal is 192, or in binary here 1100. 1100 in hexadecimal is C, and if you've just got a 1 in the two column here, so 1, 2, 4, 8, you can see that's a 2. C in hexadecimal is 12, so we've got 8, 9, 10, 11, 12. So I think we've covered hex earlier. So you swap the 7th bit, so 1, 2, 3, 4, 5, 6, 7. This bit has to be swapped if we're doing EUI64, and then it becomes a 0. If you work this out, 0, 0, 0, 0, the second part is C0. So here we go, C0, and then it carries on as normal, 0, 0, instead of C2. So I know it's a lot to get your head around. Just practice it, watch this over a few times, and then practice some of your own examples. Applying it, enter your desired subnet, and then add the command, the tag, EUI64. This is how you do it in Cisco. You won't be asked about vendors or how to apply it, I'm sure. I'm just telling you how it works. So I've added this address. I want to say we're using this subnet here, this address, and double colon, so I don't care what goes there, /64, and then I add the tag basically saying you allocate using the MAC address plus the 7th bit rule, which will swap the 7th most significant bit from a 0 to a 1 or a 1 to a 0. And here's the command on an actual router. So you can't just say create the entire address for the routable address. You have to add this tag here. Alright, next is the neighbor discovery protocol, which is a major feature of IPv6. This allows other routers on the link to be discovered. There's a couple of messages you need to be aware of, which is RS, router solicitation, like are any routers on the link. This is the router solicitation message, and it's sent out saying what else is here. The router advertisement is the reply you'll get from the routers, IPv6 routers. RA, yep, I'm here. RA, I'm here. It discovers prefixes, so whatever your prefix is on the network, etc. These routers will say we're using this prefix, and then this will be able to auto-allocate an address so it can communicate on the subnet. So this replaces ARP. We don't have ARP working on the IPv6 subnets. Also works with duplicate address detection, which I've already mentioned. The device, the IPv6 device, will say, I want to use address X. Are any of you using it? And then there'll be a reply if it is in use. So neighbour solicitation, asking for a neighbour's information. The neighbour advertisement, you advertise yourself out to neighbours. The solicitation, ask for information about local routers. These are the 4 types that you need to know about. Router advertisement, advertise yourself as active. These are the 4 types, so make a note of them. DAD I've already mentioned. The neighbour advertisements are sent to check if your address is unique. This is the address it's sent to, which is the same as the broadcast address, but we're multicasting in IPv6. No reply means your address is available to use. The amount of air seconds should vary from vendor to vendor. I haven't read the RFC actually, but if you really wanted to, you could read it. So you can see the advertisement is going out with this address. Reply if you are this address using the ICMP v6 packet. And then the advertisement here, I am this address, so basically you can't use it. DHCP version 6 is used for IPv6. This is for auto allocation of addresses. Also used with it's used in conjunction with DNS for IPv6. Here's the RFC if you've got some spare time in your hands. Allocates IPv6 information to hosts. Obviously, the IPv6 is the gateway, the DNS server, and other DHCP information. Host can request it with an outgoing router advertisement message. Allocated and requested using UDP. Bear that in mind because some people think it's TCP. It's port 546 and 547. The other subject you need to be aware of now is if you're running IPv6 on your network and then IPv4. Nobody is going to come into work one day and have IPv4 taken off and only running IPv6. You're going to have a transition period where you're running both of these protocols. So what's going to happen is somehow IPv6 host reaches an IPv4 router, and what you're going to have to do is tunnel the IPv6 information inside an IPv4 packet with a header and the trailer running IPv4. There's a few versions. ISOTAP, 6-to-4 tunneling. Dual stack is when you're running both at the same time. There's a static tunnel, I think. Yeah, that's different to GRE. You don't have to know the config, so don't worry about it. Generic routing encapsulation has been around a long time, but you can use that for tunneling. Automatic is another type you can choose from. If you want to study more, I recommend everyone needs to do about 4 hours study into IPv6. This is for interviews, technical jobs, technical interviews, and just to do your day-to-day job. You do need to understand it. There's a course on howtonetwork.com. It's 16 hours in total, but I broke it down into, I think the beginner course is about 3. There's an intermediate with loads of routing, and then maybe, I think, 5, or I'm trying to do my math now, 6, 12, 7 hours extra, which is advanced. So you could just do one part, and then when you come to do something a bit more difficult, do the second part, and if you want the third. But you really do need to know IPv6. I've been talking about this for about 4 years now, and it's becoming more and more urgent. So I used to recommend it, and now basically the level of understanding and the level of adoption is basically you have to know it. It's just like not knowing IPv4 now if you go into an interview. So please do learn it. We've covered IPv6, address types, neighbor discovery, EUI64, and then tunneling. That's all for now. Thanks for listening.
IP assigning and addressing methods. So having discussed both IPv4 and IPv6 and the difference between these different types of IP addresses, we now want to talk specifically and in more depth about how IP addresses are assigned to a specific node or client or server. So in this module, we're going to look at the two different ways that IP addresses are assigned. This involves defining the first, static IP addressing, static meaning that the IP address is always the same, and dynamic IP addressing, which means that the IP address can change. We also want to talk about the strengths and weaknesses of each of these addressing methods, and we want to compare the features of one and the other. We're also going to identify when we want to use dynamic IP addressing as opposed to static IP addressing, and define, when we're talking about dynamic IP addressing, the terms DHCP, the server and protocol that are responsible for allowing dynamic IP addressing to work, something called the scope, which lets the DHCP server know which IP addresses are up for grabs, and then the lease, which, just like the lease on an apartment, lets both the server and the client know when a IP address can be used and for how long. We also want to talk about when static IP addressing would be preferred, and as you can probably tell from the way this is worded, we generally want to use dynamic IP addressing, as we'll talk about. But there are certain instances in which a static IP addressing is the best method for us, and we'll talk about those as well. So first, let's talk about static IP addressing. It's done manually, and that's what this really means. Static means manual assignment, which means that I literally have to go to the computer and type in what the IP address is and how I want to use it. So there are two major flaws with this. First, it can be very time-consuming because it has to be done manually and each address has to be entered individually by hand. In addition, this takes a lot of time and it's prone to a lot of errors. Human error is often a factor when we're configuring addresses for a large amount of systems. And if you can imagine, I'm working in a system of, say, 5,000 computers, then I'm going to be typing in IP addresses a lot. Now, while this may be a worthwhile method when assigning a very small amount of addresses, it's obviously not very practical when I'm talking about large quantities. And the other major flaw is that it has to be reconfigured every time the addressing scheme changes. So for instance, if I was going from IPv4 to IPv6 on my internal network, I'm going to have to rechange everything once I've switched over. Or let's say I want to change my naming system. Maybe I want to go from a class C to a class A IP addressing system if I'm on IPv4. And in this case, I would have to then reconfigure everything on each computer. And you can imagine the amount of time that that's going to take. So due to its many flaws, we're really not going to use this method, static IP addressing, which means, again, manual assignment. The way you can remember that is that static does not change, right? It remains constant. And the word static, meaning not changing, is what tells us that. So we're only going to use that in specific instances, and I'll talk about that a little bit later. So as a result, it's very rarely used except in very specific instances. I'm guessing you've never had to enter the IP address on your Soho router or at your computers at home, and that's because we're going to use this other method, being dynamic addressing. Now, as the name dynamic implies, the IP address can change, which means that it is automatically assigned. Now, this is a lot more useful of the two that we have for many reasons. It's done automatically through a protocol called dynamic Host Configuration Protocol, or DHCP. So you ever hear DHCP, that is what is referred to when we're talking about dynamic IP addressing. This is part of the TCP/IP suite, and it allows a central system to provide IP addresses to client systems. Now, since it's done automatically, there's no possibility of human error, and it's also a lot more efficient than static IP addressing. As a result, it's a lot more common of a method. It also eliminates the need to reconfigure a system if the addressing scheme is changed. So it's far more commonly used because of all these reasons, like we just said. It's more practical and more efficient because I don't have to change every computer. All I have to do is tell the DHCP service computer, we'll talk about that in a second, that we're changing everything, and all the underling computers automatically are going to change. So if we move over real quickly into our Windows system, and let's go into our network properties, and we'll go ahead and go to Change Adapter Settings. I'm going to right click on this and go to Properties. Now we'll see over here, if I click on TCP/IP4 and go to Properties, it says Obtain an IP address automatically. So through DHCP, the IP address is being automatically obtained, just like DNS is also going to be given out automatically. Now, if I wanted to do it statically, I would have to manually assign an IP address, a subnet mask, and a default gateway for each device. So you can see where we're not going to want to do that. So let's talk a little bit more about DHCP, or the Dynamic Host Configuration Protocol. This is the protocol which assigns IP addresses, and it does this first by assigning what's called, or defining rather, what's called the scope. The scope are the ranges of all of the available IP address on the system that's running the DHCP service. And what this does is it takes one of the IP addresses from this scope and assigns it to a computer or a client. So for instance, let's say that we're dealing, for simplicity's sake, with a 192.168 Class C network. So the scope might be something like 192.168.1.10 through 254. This means that of the IP addresses it's going to assign, it's not going to take anything in front of the 10. So this gives us .1 through .9 to use for static IP addressing. So what this ensures is that the DHCP server is not going to assign an IP address that we have already manually or statically assigned to another device. We'll talk about why we would want to do that in a minute. But this ensures, again, that the scope, that the DHCP is not going to assign an IP address outside of its scope. Then what it does is it takes this available address and assigns it to the client for a set amount of time, and this is called a lease. So the lease says how long the IP address is going to last. Now, the reason that we had leases is because, remember, if I turn off my computer, it no longer needs an IP address. It also means that, let's say I'm taking a computer away, if it has a lease of forever, then that computer now has one of my available IP addresses. So sometimes we'll have an IP address with a 24-hour lease, or maybe a 2-day lease. But whatever that lease is, at the end of that lease, it's going to have to again ask for another IP address. This is also the way that we can share a limited number of IP addresses with a lot of computers or nodes. So when we had the internet, we used to dial up to our ISP, or internet service provider. What this would allow is it allowed our ISP to provide us with one IP address that only lasted for a certain amount of time, and then when we disconnected the IP address, or disconnected from the server and therefore didn't need the IP address, it could assign it to someone else, and it didn't have to worry about us coming back on and wanting to use the same IP address. Because remember, one of the rules is you cannot have two devices with one IP address. All right? Now, let's talk about how this works from the client's point of view. Basically, what happens is I have a DHCP server here, and it has what's called a trusted connection to the switch. We've defined what a switch is previously, and we'll talk a bit more about them later as well. But it has a trusted connection. This computer, say, comes online and says, "Hi, can I join your network? Can I get an IP address?" It sends its request through what's called an untrusted connection to wherever the DHCP server is. Now, the DHCP server at some point finds this, because this is generally a broadcast, because, again, it's not a unicast, it's a broadcast, because this computer coming on doesn't know where the DHCP server is. So it sends a broadcast message out. The DHCP server then responds and offers a lease on an IP address, at which point this untrusted or unassigned connection becomes a trusted one. Now, when the lease goes out, it's again untrusted, and so it needs to repeat the entire process again. Now, so far, we've been pretty fair to DHCP and expanded on the benefits for dynamic addressing. But there are some exceptions when a network is configured for DHCP, and we don't want every single device to be automatically assigned an IP address. For instance, the DHCP server itself needs to have a static IP address. This is because we don't want the DHCP server to be changing addresses. And what's going to happen is if we have a lease, theoretically, the DHCP server could change its IP address. And since every computer on the network needs to know where to go, that's going to have to remain the same. This is going to go the same with the domain name server, so the DNS server, which allows us to convert between, say, google.com and the IP address. So we don't want to have to find this every single time, and we have to set it as something specific, meaning static. We're also going to put our web server as some static IP address. This is the reason why, if you wanted to get an account with your ISP or internet service provider, and you wanted to run a web server from your computer at home, you would need to ask for a static IP address, because that's the only way that someone can link through DNS to your web server. And so our web servers always has to be static, because when I type in google.com, I always want it to go to one of a few different IP addresses. Finally, printers are something else that we want to have be static, because the printer we don't want to move around. We want to be able to lock it in when we install it on the computer. Same with any servers. Also, routers, the gateway computer or the gateway device that allows us to get out to the network, we need that to remain the same. So that's why when we define the scope, and in previous example we defined it as any IP address between 10 and 254, we don't want it to change, because we want these 9 IP addresses to be ones that we can assign. Now, sometimes we're going to make this a little larger, so that way we can assign a lot more static IP addresses. So also maybe a wireless access point we might want to be static, etc., etc. And all of this, again, is done through a web interface or through some sort of router device or through a terminal or something. So this is not something we're physically hardwiring onto the device, because, again, that's a MAC address, physical address. But this is something that we want to set through a software of some sort. All right, so just to recap what we talked about, we defined static IP addressing. Again, static means that the IP address does not change. It also means that it had to have been manually assigned. Okay? Now, we also talked about dynamic IP addressing, which DHCP allows us to do. And this means that the IP address can change because it is automatically assigned. One thing I didn't specifically talk about, what we referenced in previous modules too, is that a PIPA address, that automatically assigned IP address, which if the dynamic IP address system is not working, so the DHCP server, for instance, is down, and it can't get an IP address from the DHCP server, it's going to assign itself its own IP address. Do you remember that was 169.254.x.x? So if you see this is your IP address, then guess what? Your DHCP server is down. We also identify the strengths and weaknesses of each of these. So we define the static, we define dynamic, and then we identify the strengths and weaknesses of each. Remember, the strength of dynamic is that it's easy and it requires less work if we change anything. Of course, the dynamics, or the downside of it, could be this APIPA, or we don't want the IP address to change. We also talked about when to use dynamic IP addressing, which is in most cases. We define DHCP, which allows dynamic IP addressing to work. Scope, which is basically the range of IP addresses. And the lease, which is how long the IP address is going to be sent out for. And then we recognize when static IP addressing is preferred. For instance, when we're dealing with printers or routers or even the DHCP server itself, which we cannot have change. TCP/IP, TCP/IP tools and commands. So in the last module, we talked about the simple services that TCP/IP provides, and those you may or may not see on the Network Plus exam. However, in this module, we're going to talk about some of the most essential tools when it comes to the TCP/IP suite, and I can almost guarantee you're going to see these on the exam. So we're first going to discuss and demonstrate all of the TCP/IP tools. And some of these tools include the ping command, and some of these we might have seen previously as well, perhaps in A+. And some of these also I'll go into the operating system and show you. So we're going to see the ping command, which basically tests for connectivity. We're also going to look at the traceroute command, which basically traces a ping route. And remember when we were talking about protocols previously, we mentioned the ICMP protocol, the control messaging protocol. And that is what a ping and a traceroute command use, or these types of packets. So we're also going to look at a protocol analyzer, not necessarily a command line tool, but something that allows us to analyze the protocols, or rather the packets that are going in and out of a network or a system. Look at a port scanner, sort of does the same thing. We'll talk about the difference between these two. We'll also look at something called NS lookup, and if the NS doesn't ring a bell with you, that is like DNS or name server lookup, how we convert between an IP address and a fully qualified domain name, such as Google. We're also going to look at the ARP command, which allows us, just like DNS, which does a name to an IP address, ARP is what is responsible for routing and allowed us to convert between an IP address and a MAC address, or physical address. So you can see where this is really going to come into handy when we're talking about routing and switches. Finally, we're going to look at the route command, which can present us with routing tables. and is specifically more or less used when we're dealing with routers, not so much in Windows. All right, so first, the ping command. The ping tool and the ping command are extremely useful when it comes to troubleshooting and testing connectivity. Basically, what the tool does is send a packet of information, and that packet, again, is ICMP, through a connection and waits to see if it receives some packets back. This is not unlike when you used to see the radar screens on a TV or program. We're talking about with submarines, for instance, and you would see basically a submarine here, and you'd hear a ping coming off of that. So it gets its name from that sort of sound. So the data literally bounces or pings right back if there's an established connection. It can be also used to test the maximum transmission unit, or the MTUs, and remember we talked about that when we dealt with an MTU black hole, which was in a previous lesson. Now, this is the maximum amount of data packets that can be sent over a network at any one time, or the maximum size of that data packets. So using this, you can test the time it takes in milliseconds for data to travel end-to-end or to other devices on the network. And this can also be done on the local host, and you remember the local host is 127.0.0.1. That's the IP address for it. And we can test this all by opening the command prompt and typing in ping and then the IP address. So let's take a look at this for just a second. If we're here and we have our command prompt, and I wanted to type, for instance, ping 127.0.0.1, which would be the local host, I can tell that my time is less than 1 millisecond, which makes complete sense, since there should be no loss of data. It should take no time, and you can see that no loss of data right here, right? Because we're sending it there and back, and obviously we're dealing with ourselves, the local host, or the 127.0.0.1, so it shouldn't be an issue. And if we do that, notice that when I use localhost, I'm using my own name, and it's also giving the IPv6 IP address here. Now, if I clear the screen for a second, I can also, for instance, ping google.com. And you'll see that it actually sends, first it figures out what the IP address is, and then sends that, and it gives us the time that it takes to get there and back. It also gives us some statistics. For instance, it was sent, 4 of them were sent, 4 of them were received, 0 lost. And so we know that on average, this is taking 13 milliseconds to get from us to Google. And if you imagine that this was a local host, or rather a local server on my network, and I was rebooting that server, this could help me tell whether the server is back up again. And one of the things I might want to do with that, and I'm just going to use the local host right now, is use the /t switch. And what this will do is it'll continually ping the same IP address over and over again. Now, so for instance, if I was waiting for a server to come back online, this would be an easy way for me to tell whether it's come back online or not. And I could exit that by pressing Control-C. All right. So the next one I want to talk about is trace route, which actually goes hand in hand with ping because it also uses that ICMP data packet or protocol. It basically tells us the time it takes for a packet to travel between different routers and devices. And we call this the amount of hops along the network. So it not only tests where connectivity might have been lost, but it's also going to test the time that it takes to get from one end to the other end of the connection. And it's also going to show us the number of hops between those computers. So for instance, between me and Google, there might be 4 different computers. And so each one of these is called a hop. And we can measure how far the packet is traveling before it gets back to us. Now, I can also use this to test where a downed router might be or where in the connection a downed router might be. So if we go in here for a second, and let's take a look at the command prompt here. And let's say I go to traceroute google.com. Now what's going to happen is it's going to start saying all the different hops. It's going to tell me how long it takes to get from one place to the next. And we can see also where it's, so right here, we're still in New York. You can see NYC. I can probably guess this is someplace in my ISP. And now it looks like it's starting to go out, get further out, and we can see that the amount of time it's taking is also more and more. So between me and Google, you can see how far we're having to go until we finally get to the google.com web server, which would be right here. And we know it took about 10 hops. Now you can see it has a maximum of 30 hops, and we can actually set that in the switches if we need to, but I wouldn't worry about that for the exam. And just to show you what it looks like if I'm tracing the local host, you can see it only takes one hop, obviously, because, or not even a hop, because it's myself. It should be no route to get to me. Now, going away from the command line for a second, I want to talk about what's called a protocol analyzer or a network analyzer. And this is an essential tool when you're running a network. It basically gives you a readable report of virtually everything that's being sent and transferred over your network. So these analyzers will capture packets that are going through the network and put them into a buffer zone. Now, this buffer zone, just like the buffer zone we're dealing with YouTube or Netflix and buffering a video, is going to hold on to these packets. And we can either capture all the packets, or we can capture specific packets based on a filter. It can then provide us with an easy, readable overview of what is contained within each packet. This allows the administrator total control of what does and doesn't pass through the network, and can also stop potentially dangerous or unwanted pieces of data to pass through the network undetected. And so what you can see here is if this is our cloud or our network, we're going to call this a TCP IP network just because this is basically our WAN. And here, let's say I have one LAN and another LAN. I'm going to have a protocol analyzer or network analyzer in between my network and my LAN. That way I can analyze exactly what's going on. In some ways, this might also take the form of a firewall. Now, this is different from what's called a port scanner. A port scanner does exactly what it sounds like. It basically scans the network for open ports, either for malicious or for safety reasons. So it's usually used by administrators to check the security of their system and make sure nothing's left open. Oppositely, it can be used by attackers for their advantage. So if I'm on the internal, I might use a port scanner to scan my firewall to see what's going to be allowed through. I might also put my port scanner over here and have it try to come in. Alternatively, a hacker could use a port scanner to go through and scan for open ports. If there are any open ports, it can then use those to try to get into my system. So I can use it either as a white hat or as a black hat. White hat means a good hacker. Black hat means a bad hacker. Now let's get back into our command line for just a second here. The name server lookup, or NS lookup, and again, whenever you see NS, as in DNS, domain name system, you can think that it has something to do with name server or name system. It's used to basically find out what the server and address information is for a domain that's queried. It's mostly used to troubleshoot domain name service related items. And you can also get information about a system's configuration. Now, DIG actually does the same thing, but it's a little more detailed, and it only works with Unix or Linux systems. So here's an example of what the NS lookup would look like. And you can see we have NS lookup here. And then, what did we do? Well, we asked it for Wikipedia's name, and up it pops the IP address. And it also tells us whether it's authoritative or non-authoritative. Authoritative would be a DNS server that's somewhere out on the internet that is definitely has all the information. Non-authoritative means it might be a local one. So if we were to look at this for a second for ourselves, let's do NS lookup to go into the utility. And now we could, for instance, look up google.com. And it'll tell us all the different IP addresses that are available for google.com, yahoo.com, maybe even microsoft.com, CNN.com, etc., etc. So you can see all these different ones that are coming through. Now notice that CNN.com actually wouldn't let us out, and neither would Microsoft.com. That's because they're actually blocking, they're filtering out the type of ports or protocols that are going to be allowing, that are going to allow like the ICMP ping. So if we were to go out of this for a second, and by the way, you do that as Control-C, and if I tried pinging Microsoft.com, you'll notice that it actually doesn't come back. And that's because they're actually shutting out ICMP packets from going in. Now, another one related somewhat is what's called ARP, or Address Resolution Protocol. We actually talked about this previously, and it's really used to find the media access control, or MAC address, or the physical address for an IP address, or vice versa. Remember, this is the physical address. It's hardwired onto the device. The MAC address is the system's physical address, and the IP address is the one, again, assigned by a server or manually assigned. In a way, this would be like your phone number, and this would be like your social security number, which is given to you by the government. The way it does this is we're actually going to send out discovery packets in order to find out the MAC address of a destination system, and once it establishes that, it sends that MAC address to the sending or receiving computer. Now, the two computers can now communicate using IP addresses because they can both actually resolve to IP addresses. So basically, I want to send something, right? So what I'm going to do is I'm going to go out, hit a router. The router uses ARP in order to get the MAC address to the sending computer, and now we can talk directly. Because now I know what your MAC address and IP address equal. Finally, the route command is extremely handy and can be used fairly often. It basically just shows you the routing table, which is going to give you a list of all the routes, network connections, and so on, that the user has the option to then edit. Now, the reason you might want to edit it is if, for instance, in your router, you want to tell it to use one route instead of another. So an example here shows us the gateway, the mask. So draw these really quickly. And the interface, the metric, as well as the interface, and these are all numbers, so these might not mean a lot to you, but if you had a guide and you knew where they were going, if you knew what your interface was, for instance, is it a wireless interface, or was it your wired interface, that would prescribe a specific number. The gateway is going to say what gateway you need to get out, and the subnet mask. And you could actually add specific information to this to create your own routing table. And this you would do really not so much on your computer, but more if you're working on a router, say a Cisco router, so that you can tell it exactly where you want information to be routed. So just to recap, we discussed and demonstrated several TCP/IP tools, including ping, which we're really going to use to test connectivity. And remember, you want to hold on to the /T switch, which is going to do it indefinitely. Traceroute, which is going to measure the hops and can also tell you where a connection has been lost. A protocol analyzer, which is going to look at, or network protocol analyzer, which is going to look at all the protocols coming in and can actually filter them in or out. A port scanner, which can be used to show open ports, either as a security precaution or if I'm trying to infiltrate your network. The NS lookup, which is that name server, could also be DIG, by the way, which is on Unix systems. And this is going to allow me to get my IP address to a fully qualified domain name. ARP, Address Resolution Protocol, which is specifically going from IP address to MAC address. It sort of really allows routing to occur. This is really a principle in routers. And finally, the route command, which allows us to edit the routing tables and would be really useful if I was using one of my servers as a router. You're not really going to see routing or route command on the Network Plus exam, but I guarantee you'll see all these others mentioned. So now that we've finished up this very brief lesson on TCP/IP, the tools and the simple services, we're going to go into LAN administration and implementation a bit more in depth. Remote access, remote networking fundamentals. In the last lesson, we talked about wide area networks. We talked about how they can be implemented, what their benefits are, how they transfer information, some of the technologies we use, and so on and so forth. Now, in this lesson, we're going to talk more about remote networking access. Remote networking and WANs actually really go hand in hand. And if you think about it, more of what we do now, more than ever, allows us to remote in from home to the WAN, the largest WAN in the world being the wide area network of the internet, and then access our LANs at work. This really allows us to not only get stuff done, but is changing the landscape of how networking, the internet, and security have been created and how we continue to work with them. So we're going to talk about this in this module and in the next couple. But for this one, the first thing we want to do is define what remote networking really is. Then, we want to identify some of the technologies that we see in place when we discuss remote networking. These include VPN, which we've already discussed in some broad detail, or a virtual private network. Radius, which allows us to authenticate users once they connect, and TACACS, which allows us to keep it all secure. So these three are used in enterprise settings to allow someone to remote in from home and connect to the network at work. So WANs are networks that are not restrained to one single physical location. They're typically, as we've discussed, many local area networks that are joined together to create one big WAN. However, this isn't the only configuration they can have, and remote networking is something that ties in really well with wide area networks. You see, remote networking is the process of connecting to a network without being directly attached to it, or physically present at the site. In other words, a user or a group of users can remotely connect to a network without actually being where the network is established. So, if I were at home and wanted to connect to a network, say, in China, I could actually connect as though I were sitting right in an office in China without actually physically being present. This type of thing comes in handy quite a bit. Now, remote networking doesn't always happen between two very distant locations. In fact, it can be used within the same building, the same room, while traveling, and remote networking not only works on a long-distance level, but on a local network as well. For instance, suppose that I'm an administrator in my office, and I want to access the contents of a user's computer, or I want to restart a server. Well, instead of having to get up, walk up to the 4th floor, or down to the basement, wherever the server is, I could simply remote in to the server and reboot it from there. So you can see that it's a huge time-saving device. However, it also opens up a lot of possibilities for security issues and so on. So here's an example of what remote network connectivity could look like. The user is in China on the right, and they need to connect into the network in New York here on the left. So they're sitting at one physical location, and they connect through a WAN, which we're going to call the internet, the largest WAN in the entire world, and they remotely connect in some sort of way, which we'll talk about, usually through something called a VPN, using all sorts of public networks, and eventually they reach the router at their corporate office, and then it's as if they are actually sitting there connected into the network. They can now access resources on local clients or even on the server, and all without physically being at the location in New York. Now, there are a lot of terms we hear when we talk about remote networking and remote access. Most of them end up being acronyms for the sake of time and convenience. But there are three that I want to specifically talk about here that we're going to talk about in more detail in the coming modules. The first is VPN, or Virtual Private Network. This is something we've talked before and we'll talk about a little bit later, but in essence, it extends a LAN or a local area network by adding the ability to have remote users connect to it. The way it does this is by using what's called tunneling. It basically creates a tunnel through the wide area network, the internet, that then I can connect to and through. So all of my data is traveling through this tunnel between the server or the corporate office and the client computer. This way I can make sure that no one outside the tunnel or anyone else on the network can get in, and I can be sure that all of my data is kept secure. This is why it's called a virtual private network. It's virtual, it's not real, it's not physical, it's definitely private because the tunnel makes sure to keep everything out. Now the next term we want to talk about is called Radius. Radius, by the way, stands for Remote Authentication Dial-In User Service. I'm going to write that out here. Remote Authentication Dial-In User Service. Now, if you notice there's a dial-in, well, remote can actually be dialing in using a modem. We don't use that much anymore, but this is an older service. What this does is it allows us to have centralized authorization, authentication, and accounting management for computers and users on a remote network. In other words, it allows me to have one server that's going to be responsible, and we're going to call this the Radius server, that's responsible for making sure once a VPN is established that the person on the other end is actually someone who should be connecting to my network. Remember, I don't want to just let anyone connect. I want to make sure the person who connects is someone who belongs to my network. Generally, what we'll do is we'll have active directories, which is what Microsoft uses to create, for instance, usernames and passwords, and we'll link that up or sync it with the Radius server. Sometimes this is done on a separate server. Sometimes it's done on the same server. Either way, once you connect the VPN then goes to the Radius server. The Radius server checks the Active Directory, and now I can make sure that only users of the network are allowed onto my network. Finally, we have something called TACACS, or Terminal Access Controller Access Control System. It's really long, I'm not going to write it out. This is actually a replacement for Radius. There was another replacement for Radius, by the way. It was called Diameter, and if you're a math whiz, you'll notice that Radius is half of a diameter when we talk about circles. But diameter wasn't really used much. TACACS, on the other hand, is a security protocol. It allows us to validate information with the network administrator or server, and the validation is tested when we try to connect, just like with Radius. Of course, the benefit is TACACS is newer and more secure than Radius. So it basically does the same thing. It's just a little more powerful. All right, so this was short, but I just wanted to give us an overview of remote networking, and we're going to talk more about that in the coming modules. So we talked about remote networking, what it is, allowing us to access a LAN basically through a WAN, whether that WAN is the internet or a public switch telephone network. It also allows us to access the LAN from a different physical location. We can also identify 3 remote networking technologies. The first, virtual private network, creates a tunnel over the WAN through which we create a virtual network that is also private. We also talked about Radius and TACACS. Both of these allow for authentication, so we can make sure the person who establishes the VPN is actually allowed on our network. Authentication, authorization, and accounting. In the last module, we started off this lesson by discussing the fundamentals of network security. Now, a big portion of network security has to do with AAA, or authentication, authorization, and accounting. The AAA server on a network is probably one of the most important things when it comes to security, and it does quite a bit of work. So in this module, we're going to define and discuss these three A's: authentication, authorization, and accounting in further detail, so we know not just what they are, but how they're implemented in a very general way. Authentication is the first A. It's used to identify the user and make sure that the user is legitimate. Sometimes attackers and bots will try to access the network or secure data by acting like they're a legitimate user. This is where authentication comes into play. Any secure network is going to require something like a username and password to log in, and any data that's really important or secure needs to be protected. Now, there are ways, of course, for these attackers to gather the password and username information, but the smart thing for us to do is to change passwords for all users on a network frequently, probably every 30 to 90 days. Again, we have to balance that with how easy it is for someone to come up with a new password, and if they're going to remember the new password they come up with. We need to make sure that the passwords are documented in some way, although we want to be careful again, because when we write them down and document them, that opens up another way they can be stolen. And we want to make sure that they're all secure. If an attacker has an outdated password, it's going to do them no good. So if we can put this in another way, authentication verifies identity. This is sort of like you have a ID card or driver's license. That provides your identity and authenticates you are who you are. One of the reasons we have pictures on our driver's license or government-issued IDs is so that people can look at it and guarantee we are who we are. This used to be done with signatures. They would look at two signatures, make sure they were identical, and then we could authenticate the person was actually us. Now, we've moved way past this now. We can even use things like fingerprints, which more or less authenticate that we are who we say we are. So here is another form of authentication. You may have encountered this one before when you're trying to access things on the internet. This is called, or looks like, a CAPTCHA, and it's used to stop bots from accessing secure data or infiltrating someone's account or making an account when we don't want them to. So the text in the gray box is difficult to read for a bot. It's actually a picture, and it's very difficult for robots to read this and know exactly what to type in. So because of this, the CAPTCHA is usually made in different fonts, distorted text, pictures, etc., and it can be slightly different for a human to read, but not so difficult for them that they can't actually type it in. When you type in the image into here as text, then you can basically ensure that you are who you say you are, that you are a human rather than a bot. Now, authorization is the next security level after authentication. It's the second A. So once a user has been determined authentic, we've authenticated their identity, they're going to be allowed onto the network. But they can't just have free reign and do whatever they want. We want to make sure that they can only access specific things. Remember that concept of least privilege? Well, we want to make sure that the person who's on there is only going to access stuff that they are allowed to access. So you're authorized to access only certain things. Now, there are users, such as the admin, who can generally access a quite deal more. But we don't want, for instance, the administrator to have access to the partner's private email in a law firm, and we don't want someone who works in accounting to have access to marketing. So authorization basically provides the information on what the person or the ID'd person who has been authenticated is authorized to get access to. Now, authorization procedures can stop users from accessing certain data, services, programs, etc., and can even stop users from accessing certain web pages. For instance, we sometimes have filters that make sure our kids don't access very specific information unless they can type in a password that would authenticate that they're an adult. So here's an example of what a denied web page might look like. As you can see, the user is being told that an error 403 has occurred. In other words, the web page has been forbidden. It requires you to log on, and you have not logged on successfully. So you have not authenticated who you are, and therefore you are not authorized to have access to a specific degree of information. Now, users other than the administrator will most likely not be authorized to run commands in the command prompt, and we've looked at this with A+, running things in an administrator mode. If the user does, they're probably going to receive an error that looks like this. This command prompt has been disabled by your administrator. The administrator can deny every other user on the network the ability to use the command prompt because they could do something that they are not authorized to do. So it's up to the administrator to make sure that only authorized users can access the command prompt or do other things on the computer or on the network. For instance, rebooting computers, accessing servers, and so on. Now, the final A we talked about, authorization and authentication, is accounting. Accounting is not the same as in bookkeeping. It's accounting in the sense that everything a user does while on the network has to be accounted for and carefully watched. This is sometimes also called auditing. Another term that gets back to accounting in a sort of financial sense, but it means something different. The users on a network can often be one of the biggest of our security concerns. Most of the time, someone is going to hack our network from inside rather than outside. And so keeping track of how users spend their time is one of the most important aspects of network security. The accounting function of the AAA server is to do exactly that. It watches all of the users and monitors their activity, as well as all of the resources they're using. These resources could include stuff like bandwidth, CPU usage, and a lot more, not to mention what websites they're accessing and so on. Now, some people say, hey, wait, you're infringing on my right to use the internet. But if you are at your company using your company's internet, then you have signed most likely an agreement saying you're only going to use it for specific purposes. And you've probably also signed an agreement, whether you know it or not, that allows them to monitor you while you're using the internet. So here's a representation of what the accounting function of a AAA server does. It oversees everything the users are doing and keeps track of what the resources are those users are taking up and how they're spending their time. Now, this was a short module, but it discussed the AAA, and these are three really important concepts you need to know and understand for Network Plus. First, we looked at authentication. Authentication makes sure that the identity has been verified. This is just like, in a metaphor, your driver's license, which has a picture ID. Next, we talked about authorization. This is what you are allowed to do. This could be just like you're authorized, if you have your driver's license and you're 21 and up in the United States, to drink. So, authentication is provided by the driver's license. You are who you say you are. And then authorization says whether or not you're allowed to drink or even drive, depending on your age and a variety of other circumstances. Finally, accounting is basically a log of what you do. If you get in trouble with the law, that's put on a record. That way, if you're pulled over by a policeman, let's say for speeding, they can scan your driver's license and see if you have any outstanding warrants or if you've been pulled over in the past. In this way, accounting provides background information on you and can make sure that we know what you're doing on the network, what information you're accessing, and also make sure when you're accessing it, and so on. Let's say that we have someone rob our store at midnight and the store is closed. Well, if your security card was used to get access to the store, then we know that either you robbed the store or someone who stole your security card robbed your store. IPSec and IPSec policies. Having discussed intrusion detection and prevention systems, which are mostly having to do with keeping attacks and malicious software off our network, I want to talk about something called IPSec, or IP security, which is a sort of group of protocols and policies that are used to keep the data that we have secure on a network. Whenever we talk about security, there's something called CIA, the CIA triad, that we need to keep in mind. C stands for confidentiality, meaning only the people we want to see something actually see it. The I stands for integrity, meaning what we send is what the other party receives. It hasn't been tampered with. And finally, we have to balance all of this against availability. It doesn't matter if something is super secure if no one can access it. So broadening out into this, that's where IPSec comes into play. So we're going to talk about IPSec, defining and discussing what it is, and then talk about two protocols that we focus on with IPSec, AH and ESP. We're also going to discuss three different services that IPSec uses or serves. One is data verification, protection from data tampering, again getting into that integrity, and private transactions, going along with that confidentiality. All of this supports availability, and the reason we have IPSec is to make sure that in our security we have available data. Finally, I want to talk about some of the policies, the ways that we use IPSec. So as I mentioned, a good amount of the security measures that we use on a network are used to prevent attacks and shield the network from viruses and other malicious software. But not all security measures are used for the preventions of this malicious stuff. Some are intended to keep data and communications secure within a network. While preventing attacks is certainly a part of this, there are some security measures that exist to establish secure and safe communication paths between two parties. This is what IP security or IPsec protocols do. They're used to provide a secure channel of communication between two systems, or more systems. These systems can be within a local network, within a wide area network, perhaps even over a virtual private network. Now, some people might think that data traveling within a local network is secure, but this is only sometimes true. Imagine that someone has hacked into our network and we're sending data across it. Well, now we want to make sure that the data itself is secure. So while the entire network might be protected by firewalls, antivirus, IDS, IPS, there might be nothing protecting the actual connection between the two users. Generally, the data that gets sent across the network is not really heavily protected, or didn't used to be. So people tend to think that just because their network has a shield around it, everything inside it is safe as well. But this isn't the case. It's important to have IPsec protocols in place to secure the data sent and the connections made over a network, both local and wide area networks. Now, there are two main protocols that are categorized in IPsec. They are AH, or Authentication Header, and ESP, the Encapsulating Security Payload. Let's talk a little bit more about what these are. As the name states, AH, or Authentication Header, is used to authenticate connections made over a network. It does this by checking the IP address of the users that are trying to communicate and make sure that they're trusted. It also checks the integrity of the data packets that are being sent. In other words, is this the data that we actually intended, and was it received properly? The other one, Encapsulating Security Payload, or ESP, is used for encryption services, which I think we've talked about. It encrypts data that's being sent over a network using AH to authenticate the users. ESP will only give the keys to the users that have been authenticated. So I make sure to authenticate using AH that this is the user I want to give something to, and then the ESP does the encryption for the people who have been authenticated, providing keys only to the people who meet the first condition. Now, if this seems like a broad overview of these two, it is. We're not going to see this a whole lot on the Network Plus exam, maybe one question, but it's not really worth going into depth because that's what Security Plus is going to do. And when you talk about Security Plus, you're really going to talk about these and IP security in more depth then. Now, there are a few benefits and services that IPsec protocols provide. The first service is data verification. This service ensures that the data that is being sent across the network is coming from a legitimate source or a legitimate place. They make sure that the end users are the intended users, and they keep an eye on packets as they travel across the network. The next service that IPsec is going to provide is protection from data tampering. Again, that integrity. The service makes sure that while data is in transit, nothing changes. This could mean the data somehow becomes corrupted or that someone literally tampers with it. Again, while IPsec protocols provide secure communications within the network, they don't actually stop an attacker from entering the network. So while there is a chance of an attacker on the network, they can't tamper with the data as it travels through, because IPsec is going to make sure that doesn't happen. Finally, IPsec provides private transactions over the network. This means that data is unreadable by everyone except the end users. This is where that authentication comes in, and where confidentiality comes into play. For example, if Mike and Steve have to send some private banking information to each other, the service makes sure that Mike and Steve are the only people who can read it. This isn't happening at any level that you can see. It's happening all within the protocols that already exist. When we talked much earlier about IP version 4 versus IP version 6, one of the great benefits of IP version 6 is it has all the IPsec stuff built in. So all of this is happening automatically within our new version of IP version 6. It's not even something we need to really worry about, just something we need to know is taking place so we can be a little more sure that our data is actually being secured. So here is what IPsec might look like if they were connecting two LANs to make a WAN. Though the two networks have their own firewalls and protection systems, they still have to connect through a public network, which we know isn't the safest thing. This is especially true when the public network is the internet. Now, using IPsec, the two LANs are going to create a tunnel of communication through the network, or through the internet. This tunnel is secure and only accessible by people inside their network. This IPsec tunnel, by the way, is what we're referring to when we talk about VPN or virtual private networks. So when we set up IPsec, the service doesn't just configure itself necessarily. There are some things that have to be put into place for the services to run properly. These are called policies. And policies is what configures the services that IPsec provides. They're used to provide different levels of protection, data, and connections based on what is getting passed through them. In other words, just like with passwords, we have the passwords and we know they're built into Windows, but unless we set some sort of policy that tells the users how their passwords have to function, they might not be used very well. Someone might just use the password, which isn't even a safe password. So we have a password policy that ensures that people have a certain length, history, and certain characters included in their passwords. The same thing sort of goes with IPsec. Now, there are some important elements that we have to address when setting up IPsec policies. First, we have filters that are put into place. The filters determine which packets should be secure and which can be left alone. Now, every filter addresses a different type of packet, so there's generally a good amount of different types of filters. All of these filters get compiled into a filter list, where the administrator can easily change and reconfigure the filters to address the needs of their network. Now again, the reason we're going to want to have filters is because the more security, just like the more layers you have on if it's cold outside, the more data it takes up, and the longer it takes to decode. So the less security we have, the faster the data is going to travel, but the more security, the less easy it is to tamper with. So we need to weigh this. Stuff like browsing on the internet might not be something we need to secure a lot, whereas we probably want to secure, for instance, email a lot more, or even bank social security numbers, etc., etc. Next, policies have to be provided the proper network information. This involves what security methods, connection types, and tunnel settings are being used. The security methods are basically algorithms that are used in encrypting and authenticating the data. Connection types determine whether the policies are going to handle a local area network, a WAN, or a VPN. In other words, IPsec needs to know what type of connection I have here, so it knows what level of security to put into place. You can imagine that with a wide area network or a VPN, we need more security than with a LAN. Alright, so although this might have been short in duration, we covered a lot of important things. First, we talked about the fact that IPsec exists. remember, IPSec stands for IP security, and it's really not its own protocol. What it is a series or a group of protocols, services, etc., that ensure security over the IP protocol or the Internet protocol. We also talked about two of the ways we do this. One is the AH protocol and one is the ESP protocol. Remember, AH stands for Authentication Header. As the name implies, it's a header in the IP packet that authenticates to make sure the users who are about to communicate are the ones for whom it's intended and who are sending. ESP, on the other hand, which stands for Encapsulating Security Payload, is literally going to encapsulate the data in an encrypted form. And it'll only release this encrypted information to someone who has been authenticated to receive it. And remember, to do this, we use keys, both public and private. We also discussed the three different IPsec services that are provided, including data verification, which ensures that the data packets being sent are coming from legitimate places. Protection from tampering, which ensures the integrity of our data, that it has not been tampered with, either tampered with from, say, an attacker, or the data might have just become corrupted. Finally, we ensured that we're having private transactions, meaning that the data is confidential between only the people who need to be having it. And lastly, we discussed IPsec policies, some of the things that we need to have when we're creating our policies for IP security. For instance, we need to know the type of network we're on, and also filters, so that the appropriate level of security can be applied to the appropriate type of data.